What if everything we believe about the age of civilization is wrong, not by centuries but by hundreds of millions of years? What if beneath the thin, fragile layer of soil on which we have built our cities and written our histories, there exists a silence so deep and so ancient that it holds the memory of minds we have never imagined? Tonight, let this question settle over you like a low fog. Let your body sink into whatever softness surrounds you. Let your breath slow. And before you allow yourself to drift completely into this stillness, take a moment to like this video and subscribe, but only if you truly enjoy what we do here. And if you feel like sharing, tell us in the comments where you are listening from tonight, and what time it is where you are. Now close your eyes, or let them rest, and let us walk together into a question the world has barely begun to ask. The Earth is 4.5 billion years old. That number is spoken so often it has lost its power, the way a word repeated endlessly becomes just a sound. But consider what it actually means. If the entire history of the planet were compressed into a single calendar year, with the formation of the Earth on January 1st and the present moment falling at midnight on December 31st, then the whole of recorded human history, every pharaoh, every empire, every war, every poem, every monument, would occupy the final fraction of a second before the clock strikes 12. Not a day, not an hour, not even a full second. A sliver so thin it would be invisible if drawn on a page. In that vast expanse of time, continents have drifted and collided, and broken apart again. Oceans have opened and closed. Mountain ranges have risen to Himalayan heights, and been ground to nothing by wind and rain. The atmosphere itself has been rebuilt more than once. Oxygen levels have surged and collapsed. Ice ages have locked the planet in white silence, and volcanic epochs have turned the sky to sulfur. Life has emerged, flourished, been obliterated to near totality, and emerged again, each time in forms so different from what came before that if you could travel back you would not recognize your own world. And through all of this we have assumed, quietly, confidently, without ever really examining the assumption, that intelligence happened only once. That consciousness, the capacity to shape the environment with deliberate intention, to build, to record, to wonder, is a singular event in the history of this planet. That it belongs to us and to no one before us. But what if that assumption is not a conclusion? What if it's simply a reflection of what we have never thought to look for? In 2018, two scientists published a paper that asked precisely this question, not in the fringe press, not in a blog or a late-night documentary. It appeared in the International Journal of Astrobiology, authored by Gavin Schmidt, the director of the NASA Goddard Institute for Space Studies, and Adam Frank, a professor of astrophysics at the University of Rochester. They called it the Silurian Hypothesis, a name borrowed almost playfully from a fictional race of ancient intelligent reptiles in a British science fiction series. But the question they raised was not playful at all. They asked, if an industrial civilization had existed on Earth millions of years before the emergence of humanity, what evidence of it would remain? What traces could survive the grinding, erasing machinery of deep geological time? And perhaps more unsettling, would we even recognize those traces if we found them? The paper did not claim that such a civilization existed. It made no extraordinary assertions. What it did was something far more destabilizing. It demonstrated that our confidence in being the first intelligent inhabitants of this planet is not based on evidence. It is based on absence. And in science, the absence of evidence is not evidence of absence. It is simply the shape of what we have not yet examined. Think about that for a moment. The certainty that human beings are the first technological species to walk this earth is not something that has been tested, measured, or confirmed. It is an assumption embedded so deeply in every discipline, in geology, in paleontology, in archaeology, in the philosophy of history, that it has become invisible. It is the wallpaper of the room in which we think, and Schmidt and Frank, quietly and carefully, asked what would happen if someone peeled it back. The answer, it turns out, is more disturbing than the question, because the mechanisms that preserve history in stone, the processes of fossilization, sedimentation, geological layering, are not reliable archives. They are fragmentary, biased, and in many cases actively destructive. The Earth does not remember everything. It does not even remember most things. The geological record is not a library. It is a shredder that occasionally accidentally lets a page slip through. And so the question lingers not as science fiction, but as a gap in our knowledge so large that it could contain entire worlds. Worlds that rose and fell and left behind nothing we would know how to find. Worlds that may have asked the same questions we're asking now, and whose answers, if they ever arrived, have been folded back into the stone, into the silence, into the deep, indifferent time that holds everything and tells us almost nothing. What remains then, when a civilization is given not thousands of years to decay, but tens of millions? What whisper could possibly survive that long? And if such a whisper existed of updates, a faint chemical anomaly, a strange ratio of isotopes in a layer of ancient rock, would anyone be listening? The whisper, as it turned out, did not come from the stone. It came from a conversation between two scientists who had no reason to be asking the question at all, except that one of them could not stop thinking about it. Adam Frank was not searching for lost civilizations. He was studying climate change on other planets, trying to understand how the development of industrial energy use might alter a world's atmosphere in ways that could be detected from light years away. It was astrobiological work, outward-looking, aimed at the stars. But somewhere in the process of modelling what alien industrial signatures might look like in the atmosphere of a distant exoplanet, a thought crept in, one of those thoughts that arrive sideways, uninvited, and refuses to leave. If we are looking for signs of technological civilizations on other worlds, he wondered, have we ever looked for them on our own? He brought the question to Gavin Schmidt. Schmidt was not a paleontologist or an archaeologist. He was a climate scientist, the director of the NASA Goddard Institute for Space Studies, one of the most prominent researchers in the field of climate modelling. His work dealt with data, temperature records, atmospheric composition, the physics of planetary systems over time. He was not someone inclined towards speculation, but the question Frank posed was not speculative. It was methodological. It asked not whether a prior civilization had existed, but whether the tools of modern science would be capable of detecting one if it had. The distinction matters. It is the difference between asking whether ghosts are real and asking whether your camera could photograph one if it were. The first question is metaphysical. The second is technical, and Schmidt and Frank were asking the technical question. They named their inquiry the Silurian Hypothesis, borrowing the term from the long-running British television series Doctor Who, in which an ancient race of intelligent reptiles called the Silurians is discovered living beneath the Earth's surface, having preceded humanity by millions of years. The name was deliberately chosen to be slightly whimsical, a way of signalling that the authors were aware of how unusual the question sounded. But beneath the lightness of the label, the substance of the paper was rigorous, careful, and deeply unsettling. Their central argument was this: the geological record is not a complete archive of life on Earth. It is a radically incomplete one. The vast majority of species that have ever lived left no fossils at all. Soft-bodied organisms, creatures that lived in environments hostile to preservation, entire ecosystems that flourished in upland forests or arid plains. These are largely invisible to paleontology. What the fossil record preserves is a narrow, biased sample, mostly hard-shelled marine organisms, mostly from shallow coastal environments, mostly from periods when sedimentation rates happen to be favourable. Everything else is silence. Now extend that logic. If the fossil record struggles to preserve the bones of a dinosaur, a large, hard-boned creature that existed in vast numbers across tens of millions of years, what chance would it have of preserving the artifacts of a civilization? A civilization by its very nature is a localized phenomenon. It occupies a fraction of the planet's surface. It exists for a fraction of geological time. Its artifacts, no matter how durable they seem to us, and steel, concrete, glass, plastics are, on geological timescales, ephemeral. They corrode, they fragment, they dissolve. They are subducted beneath tectonic plates or metamorphosed beyond recognition by heat and pressure. Schmidt and Frank calculated that the entire duration of human industrial civilization, roughly 300 years, from the onset of the Industrial Revolution to the present, would appear in the geological record as a layer of sediment approximately the thickness of a pencil line. A pencil line in a column of rock that stretches for miles. And within that pencil line, the physical artifacts themselves, and the buildings, the machines, the roads, would be almost entirely gone. What might remain would be subtler, chemical signatures, anomalous concentrations of synthetic molecules, unusual ratios of carbon isotopes, a brief, strange pulse in the deep record of the planet. The paper was published in 2018 in the International Journal of Astrobiology, a peer-reviewed publication associated with Cambridge University Press. It was not fringe science. It was not conspiracy theory. It was a formal, methodical inquiry into the limits of what we can know about the deep past, written by credentialed scientists and subjected to the full rigour of academic review. And yet it asked a question that most scientists had never considered, not because the question was foolish, but because the assumption it challenged was so deeply embedded that it had become part of the structure of thought itself. That assumption, that Homo sapiens is the first and only technological species in Earth's history, is not something that has been proven. It is something that has been taken for granted. It is the default position of every scientific discipline, not because evidence supports it, but because no one has systematically looked for evidence against it. And this is the quiet revolution of the Silurian Hypothesis. It does not claim to have found anything. It claims that we have never looked. Consider what that means. We have spent decades scanning the skies for radio signals from extraterrestrial civilizations. We have built telescopes capable of analysing the atmospheric composition of planets orbiting distant stars. We have launched probes to Mars to search for microbial life in ancient riverbeds. And yet we have never, not once, not systematically, not with any serious funding or institutional support, examined the deep geological record of our own planet for signs of a prior technological species. The irony is almost architectural. We look outward with extraordinary ambition and inward with extraordinary blindness. We search for intelligence on worlds we have never visited, while ignoring the possibility that intelligence may have already flourished and vanished on the one world we know intimately. And the reason for this blindness is not malice or conspiracy. It is something more mundane and more powerful. It is the tyranny of the unasked question. When an assumption is universal enough, it stops being visible. It becomes the air in which inquiry breathes, and no one thinks to examine the air. Schmidt and Frank did not claim to have the answer. They claimed to have identified the question, and the question once heard is not easily forgotten. If a civilization rose on this planet 100 million years ago, a civilization that burned fuel, altered its environment, perhaps even reached for the stars, what would remain of it now? Would it be a layer of strange chemistry in a core sample pulled from the ocean floor? Would it be an inexplicable spike in carbon dioxide buried in the sedimentary record? Would it be something we have already found but did not recognize because we were not looking, because we did not believe there was anything to find? The paper ends not with a conclusion but with a call, a quiet, almost humble invitation to look, to examine the geological record with fresh eyes, to ask not what we expect to find, but what we might have missed. It is a door left open, and through it comes a draught of cold, ancient air, carrying with it the scent of something vast and unresolved. The question now was no longer whether such evidence could exist. The question was whether the record of the Earth, that enormous, layered, partially destroyed archive of everything that has ever happened on this planet had already been speaking in a language no one had learned to hear. A language no one had learned to hear, but perhaps the deeper problem is that the medium itself is almost mute. The fossil record, that vast and celebrated archive upon which so much of our understanding of life's history depends, is not the meticulous chronicle it is often imagined to be. It is not a library carefully cataloguing every creature that ever lived. It is something far more capricious, far more selective, and far more salient than the textbooks suggest. To understand why the Silurian hypothesis carries the weight it does, one must first understand how little the Earth actually remembers. Fossilization is not a natural consequence of death. It is an accident. A profoundly unlikely accident that requires a precise and improbable sequence of conditions. An organism must die in the right place at the right time under the right circumstances. It must be buried rapidly before scavengers and bacteria can dismantle it. The sediment that covers it must be of the right composition, fine-grained enough to capture detail, chemically suitable for mineral replacement. The burial site must then remain undisturbed for millions of years, avoiding the tectonic forces that fold and crush and metamorphose rock beyond recognition. And even after all of this, the fossil must somehow find its way back to the surface through erosion or excavation at a moment when someone is looking for it. The odds against any individual organism becoming a fossil are staggering. Some paleontologists have estimated that fewer than 1 in a billion bones ever fossilizes. Others suggest the number is even smaller. The entire fossil record, every dinosaur skeleton in every museum, every trilobite pressed into every slab of shale, every ammonite coiled in every cliff face, represents a vanishingly small fraction of the life that has existed on this planet. It is not a record, it's a series of scattered, accidental postcards from a world that wrote billions of letters and burned almost all of them. And the biases within this record are profound. The overwhelming majority of known fossils come from marine environments, particularly shallow continental shelves where sedimentation rates are high and conditions for preservation are favourable. Terrestrial organisms, creatures that lived on land, in forests, in mountains, in deserts, are dramatically underrepresented. This is not a minor statistical skew, it is a fundamental distortion. The fossil record tells us a great deal about life in ancient seas and relatively little about life on ancient land. Entire ecosystem, entire evolutionary lineages, entire chapters of the story of life on Earth are simply missing, not because they did not exist, but because the conditions for their preservation did not arise. Consider the concept that paleontologists call Lazarus taxa. Species or groups of species that appear in the fossil record vanish for millions of years, and then reappear, seemingly from nowhere. The coelacanth is perhaps the most famous example. This ancient fish was known from fossils dating back hundreds of millions of years, and the record showed it disappearing approximately 66 million years ago, the time of the great extinction that ended the Mesozoic era. It was declared extinct, it was mourned in the ways scientists mourn lost lineages, with papers and classification notes and a closing of the file. And then, in 1938, a living coelacanth was pulled from the waters off the coast of South Africa, as alive and indifferent to its own supposed extinction as the ocean that held it. The coelacanth did not come back from the dead. It had been there all along for 66 million years, living in deep waters where the conditions for fossilization simply did not exist. Its absence from the record was not evidence of its absence from the world, it was evidence of the record's blindness. And if the fossil record can lose track of a large, bony, long-lived fish for 66 million years, what else has it lost? What else is swimming in the dark spaces between the pages of stone? This question becomes even more pointed when one considers what a technological civilization would leave behind compared to a biological organism. A dinosaur has bones, hard, minerite-rich structures that resist decay under the right conditions. A coral has a calcium carbonate skeleton. A tree has lignified wood. These are the materials that the fossil record is built from. Durable, mineralizable structures that can survive the initial assault of decomposition. But a civilization does not leave bones. It leaves artifacts. And artifacts on geological timescales are astonishingly fragile. Steel oxidizes. Aluminum corrodes. Glass devitrifies. Concrete calcium leaches and crumbles. Plastics, which we think of as nearly indestructible in our daily experience, fragment under ultraviolet radiation and mechanical stress, breaking into smaller and smaller particles until they become indistinguishable from the sediment around them. Even stone monuments, the most durable artifacts any human civilization has produced, would be unrecognizable after a few million years of weathering, erosion, and tectonic activity. The Great Pyramid of Giza, that monument to permanence, would be a low mound of sand in 10 million years. In 50 million years, it would be nothing at all. And this is the heart of the problem. The Silurian Hypothesis does not require us to imagine a civilization of impossible durability. It requires us to recognize that even our own civilization, the most materially prolific society in the history of the planet, a species that has reshaped the surface of the Earth, filled its atmosphere with novel gases, and scattered synthetic materials across every continent and ocean, would leave almost no physically recognizable trace after a sufficient passage of time. The buildings would be gone, the roads would be gone, the satellites, the cars, the computers, the 10 billion smartphones, all of it reduced to a thin, chemically unusual layer in a column of sedimentary rock. If that is true of us, a civilization of 8 billion people occupying every continent, consuming resources on an industrial scale, and generating waste at a rate unprecedented in planetary history, then what of a smaller civilization? What of a species that numbered in the tens of millions rather than the billions? What of a society that existed for 100,000 years rather than 10,000, but did so 300 million years ago, when the continents were arranged in configurations we would not recognize, when the oceans covered different basins, when the very rocks that might have held the evidence have long since been recycled by the slow, relentless churning of the planet's interior? The fossil record cannot answer this question because the fossil record was never designed, if design is even the right word for so haphazard a process, to preserve the traces of intelligence. It preserves shells and bones and teeth. It preserves the hard parts of organisms that lived in the right environments at the right times. It does not preserve intention. It does not preserve thought. And it does not preserve the delicate, impermanent structures that thinking beings create to house their lives and their meanings. So when we say that there is no evidence of a prior civilization in the geological record, what we are really saying is something far more modest and far more honest. We have not found such evidence in a record that is spectacularly ill-suited to preserving it. The silence of the stones is real, but silence, as any detective knows, is not the same as denial. Is simply the sound of a question that has not yet found its voice. And somewhere in the deep layers of this planet, in the compressed darkness of formations that have never been drilled, in the ocean floors that have never been sampled, in the metamorphic cores of mountains that have been folded and refolded beyond recognition, somewhere in all of that silence there may be an answer, waiting, not shouting, not announcing itself, just lying there, patient and small and strange in a language written in molecules rather than words, waiting for someone to ask the right question in the right place at the right time. But even molecules have their limits, even chemistry fades. And the question that follows naturally from the silence of the fossil record is perhaps the most humbling one of all. Not what the Earth remembers, but how thoroughly, how efficiently, how completely it forgets. How completely the Earth forgets. This is not a metaphor. It is a process. Mechanical and indifferent, and it has been studied with a precision that borders on the disturbing. In 2007, the journalist Alan Weisman published a book called The World Without Us, in which he posed a deceptively simple thought experiment. If every human being on the planet vanished tomorrow, what would happen to the world we left behind? The answer he arrived at, drawing on the expertise of engineers, biologists, geologists, and material scientists, was not comforting. It was a meticulous chronicle of erasure, a timeline of forgetting so thorough that it reads less like speculation and more like prophecy. The first things to fail would be the systems that require constant maintenance. Within hours of humanity's disappearance, the pumps that keep groundwater from flooding the New York City subway system would stop. Within days, the tunnels would fill. Within weeks, the freeze-thaw cycle of winter would begin cracking the streets above as water seeped into every joint and crevice and expanded into ice, splitting asphalt and concrete with the patient, unstoppable force of crystallization. Vegetation would follow the water, roots threading through every fracture, widening every gap. Within a few decades, the skyline would begin to change, not through dramatic collapse, but through the slow, quiet invasion of biology reclaiming what was briefly taken from it. Steel, that symbol of industrial permanence, would be among the first casualties. Without the protective coatings and climate-controlled environments that preserve it, steel oxidizes rapidly. The iron in its structure combines with oxygen and water to form rust, a process that is not merely cosmetic but structural. The skeleton of a modern skyscraper exposed to the elements would lose its integrity within 2 to 3 centuries. The buildings would not fall all at once. They would sag lean, shed their glass skins in glittering cascades, and eventually fold into themselves, leaving mounds of rubberdale that would, over millennia, be colonized by soil and forest. 1,000 years after humanity's departure, Manhattan would be unrecognizable. 10,000 years, and it would be a wooded island again, its grid of streets remembered only in the faintly geometric patterns of tree growth, where old foundations altered the drainage of the soil. Concrete, which we pour in quantities so vast that it is now the most abundant manufactured material on Earth, would fare somewhat better than steel, but not by much. Concrete degrades through carbonation, the slow reaction of its calcium compounds with carbon dioxide in the atmosphere, and through the mechanical assault of water, ice, and biological activity. The Hoover Dam, one of the most massive concrete structures ever built, might endure for 10,000 years, perhaps longer. But in geological terms, 10,000 years is a heartbeat. It is the time between 2 pulses of a glacier. It is nothing. And what of the materials we consider truly permanent? Glass dendrifies over millions of years, its amorphous structure slowly crystallizing, losing its transparency, becoming indistinguishable from natural mineral formations. Ceramics are more durable. Fired clay can persist for extraordinary periods, but even ceramics are subject to chemical weathering to the slow dissolution of their silicate bonds by slightly acidic groundwater. Given enough time, even the most carefully crafted porcelain returns to the mud from which it was shaped. Weisman's timeline is relentless. After 50,000 years, most traces of human habitation would be gone from the surface of the Earth. The great dams would have silted up or been breached. The roads would have vanished beneath vegetation and sediment. The cities would be archaeological sites. And then not even that. Just faintly anomalous zones in the soil where the chemistry is slightly different from the surrounding landscape, where concentrations of certain metals are inexplicably elevated, where the ratio of calcium to silicon in the clay tells a story that no one is left to read. But the truly haunting part of Weisman's analysis is not what disappears, it is what remains. And what remains is not what we would expect. It is not our monuments or our machines. It is our chemistry, the synthetic molecules that industrial civilization has released into the environment, chlorofluorocarbons, polychlorinated biphenyls, certain long-chain polymers, perfluorinated compounds. These are the most durable legacy of human existence. Some of these molecules have no natural analogue. They do not occur in any geological process. They are in the strictest sense signatures of technological activity, and some of them could persist in sedimentary deposits for millions of years. This is precisely the kind of evidence that Schmidt and Frank identified in their paper. Not buildings, not tools, not bones or books or hard drives. Chemistry, the ghost of a civilization, if it survives at all after tens of millions of years, would not be a ruin. It would be a ratio, an anomaly in the isotopic composition of a layer of ancient rock, a spike in the concentration of synthetic compounds in a core sample pulled from the deep ocean floor, a brief, strange perturbation in the chemical story of the planet, a hiccup in the data, a line on a graph that does not quite fit the expected pattern. And here is where the thought experiment turns from unsettling to vertiginous, because Weismann's analysis was based on our civilization, a civilization of nearly 8 billion people, occupying every continent, burning fossil fuels at a rate of approximately 10 billion metric tons of carbon per year, producing synthetic chemicals by the hundreds of thousands of tons, reshaping the surface of the planet on a scale visible from space. This is, by any measure, the most materially impactful civilization imaginable. And yet, given 56 million years, the timescale that Schmidt and Frank used as their benchmark, even this civilization would be reduced to a whisper in the rock. Now imagine a smaller civilization, a species that numbered not in the billions, but in the millions. A society that existed not on every continent, but on one or two, in a world where the continents themselves were arranged differently, where the climate was warmer, where the ice caps did not exist, where sea levels were hundreds of feet higher than today. Imagine a civilization that lasted not for 10,000 years, but for 100,000, but did so in the Mesozoic or the Paleozoic, in an era so remote that the very rocks that witnessed it have been subducted into the mantle and reforged in the planet's interior heat. What would remain of such a civilization? Perhaps nothing recognizable, perhaps nothing at all, or perhaps, and this is the thought that refuses to quiet itself, perhaps something, a faint chemical signature, an unexplained isotopic excursion, a thin layer of unusual sediment in a place where no natural process can fully account for its composition. Something that has already been found, already been catalogued, already been filed away under the heading of natural variability or measurement error or unexplained anomaly, because no one was looking for what it might actually represent. We have mapped the surface of Mars with greater resolution than we have mapped the ocean floors of our own planet. We have searched for biosignatures in meteorites that fell from space while ignoring potential technosignatures in the sediment beneath our feet. And the reason is not a lack of technology or capability. It is a lack of imagination, or rather, an excess of assumption. We assumed we were first. We assumed the Earth had nothing to tell us about intelligence before our own, and so we never asked. We never looked. We built our sciences on a foundation that included, as a silent axiom, the premise that the deep past was empty of minds. But Weismann's work and the work of Schmidt and Frank and the slow accumulation of evidence from a dozen different disciplines all point toward the same uncomfortable truth. We do not know that the deep past was empty. We only know that we have never checked. And the mechanisms of erasure are so thorough, so patient, so geologically efficient, that the absence of evidence cannot be taken as evidence of absence. The Earth is not a museum. It is a machine that consumes its own exhibits, and the question that now rises, quiet and insistent, is whether somewhere in the vast unexamined archive of the planet's chemical history there is already a signal, faint, ambiguous, easily dismissed, that someone, something was here before us and was forgotten so completely that even the forgetting was forgotten. There is, as it happens, such a signal. It is 56 million years old. It is one of the most dramatic and least understood events in the geological record, and it has a name. It's called the Paleocene-Eocene Thermal Maximum, and among those who study the deep history of Earth's climate, it is spoken of with a kind of quiet reverence, not because it is beautiful, but because it is bewildering. It occurred approximately 56 million years ago, the boundary between two geological epochs, and it represents one of the most rapid and extreme episodes of global warming in the entire Cenozoic era. Within a geologically brief window, perhaps 20,000 years, perhaps less, global temperatures surged by 5 to 8 degrees Celsius. The oceans warmed from surface to abyss. The deep sea, which today hovers just above freezing, reached temperatures comparable to a modern subtropical lagoon. Ice, wherever it existed, vanished. Sea levels rose dramatically. The chemistry of the ocean shifted so profoundly that vast swaths of the deep sea floor dissolved, as acidified water ate through the calcium carbonate shells of countless organisms that had settled there over millennia. The cause, according to the prevailing scientific understanding, was a massive and rapid release of carbon into the atmosphere. The isotopic signature is unmistakable, a sharp negative excursion in carbon-13 values found in marine sediments worldwide, indicating that an enormous quantity of isotopically light carbon entered the open atmosphere system. Geological instant. The amount of carbon involved has been estimated at between 2,000 and 7,000 gigatons, a quantity so large that it dwarfs anything in the recent geological record, and yet small enough that its source remains a matter of intense debate. The conventional explanations are varied, and none of them is entirely satisfying. One hypothesis points to the destabilization of methane clathrates, vast deposits of methane ice locked in ocean sediments, which can release catastrophic quantities of greenhouse gas if ocean temperatures rise past a critical threshold. Another invokes volcanic activity, specifically the eruptions associated with the North Atlantic igneous province, which may have injected carbon dioxide into the atmosphere through contact metamorphism of organic-rich sediments. A third suggests the desiccation and oxidation of massive peat deposits. Each of these mechanisms is plausible. Each has supporting evidence. And yet each also has significant weaknesses, and no single explanation has achieved consensus. What is striking about the PETM is not merely its magnitude, but its speed. Geological processes, volcanic outgassing, the slow weathering of silicate rocks, the gradual accumulation or release of ocean carbon, typically operate on timescales of hundreds of thousands to millions of years. The PETM carbon release, by contrast, appears to have occurred over a period that may have been as short as a few thousand years. Some studies, analysing the fine layering of deep-sea sediments, have suggested the initial pulse may have been even faster, perhaps just a few centuries. This is not the pace of geology. This is something else. Something that behaves less like a slow planetary process and more like an event, sudden, concentrated, and anomalous. It was this anomaly that caught the attention of Schmidt and Frank. In their paper, they noted that the isotopic signature of the PETM bears a resemblance, not identical but structurally similar, to what one might expect from the rapid burning of fossil fuels by an industrial civilization. The negative carbon-13 excursion, the speed of the carbon release, the associated warming, the ocean acidification, these are, in broad outline, the same phenomena that climate scientists project for our own civilization's impact on the planet over the coming centuries. The parallel is imperfect, as all analogies across deep time must be. The PTM carbon release was slower than modern anthropogenic emissions. The total quantity was different. The recovery took over 100,000 years, but the structural similarity is there, lurking beneath the data like a shadow that shifts when you try to look at it directly. Schmidt and Frank were careful. They did not claim that the PTM was caused by a prior civilization. They explicitly stated that natural explanations were not only possible but probable. What they argued was subtler and in some ways more radical. They argued that the PETM is the kind of event that a prior industrial civilization might produce, and that our current analytical methods would struggle to distinguish between an industrial cause and a natural one at a temporal remove of 56 million years. The signal, they suggested, would be the same. The chemistry would be the same. The isotopic fingerprint would be the same. And so the interpretation would default, as it always does, to the natural explanation, not because the natural explanation has been proven, but because no one has considered the alternative. This is a deeply uncomfortable idea, and it is worth sitting with its discomfort rather than rushing past it. It does not ask us to believe anything extraordinary. It asks us to acknowledge something ordinary but overlooked, that our methods of reading the geological record are calibrated to detect natural processes and only natural processes. The interpretive framework of geology, paleoclimatology and geochemistry does not include the possibility of technological causation as a variable. It is not part of the model, and if it is not part of the model, it cannot appear in the results, no matter how much data is collected, no matter how precisely the measurements are made. There is a concept in the philosophy of science called theory-ladenness, the idea that observation is never neutral, that what we see is always shaped by the theoretical framework through which we look. A geologist examining the PETM carbon excursion sees a volcanic event, or a methane release, or a tectonic trigger, because those are the categories available to her. She does not see an industrial signature because that category does not exist in her discipline. It is not that she has examined the evidence and ruled it out. It is that the thought has never entered the room. The door to that possibility is not locked. It is simply not visible. It is hidden behind the furniture of a century of assumptions about what the deep past can and cannot contain, and the PETM is not the only such event. The geological record contains several episodes of rapid carbon release and associated warming that remain imperfectly understood. The Eocene Thermal Maximum 2, approximately 53.5 million years ago. The smaller hyperthermal events scattered through the early Eocene. Each one shows a similar pattern, a sharp isotopic excursion, a pulse of warming, a recovery. Each one has been attributed to natural causes, and in each case, the attribution is reasonable but incomplete. The mechanisms proposed can explain part of the signal, but rarely all of it. There are always residuals, always components of the data that do not quite fit, that are filed under uncertainty and set aside for future investigation. Schmidt and Frank did not suggest that all of these events are evidence of prior civilizations. They suggested something more measured and more provocative, that these events represent the kind of geological signature that should be examined with fresh eyes, using analytical techniques specifically designed to detect technological rather than natural causation. They proposed looking for synthetic molecules, compounds that do not occur in nature and could only be produced by industrial chemistry. They proposed examining the distribution of transuranic elements, atoms heavier than uranium, which are produced almost exclusively by nuclear processes. They proposed refining isotopic analysis to distinguish between the gradual carbon release of volcanic degassing and the rapid concentrated release of fossil fuel combustion. None of this has been done, not because it is impossible, but because it has not been funded. Not because the methods do not exist, but because the question has not been asked with sufficient institutional weight to command resources. The PETM remains, in the scientific literature, a natural event with natural causes. And it probably is exactly that, but the word probably is not the same as the word certainly. And the gap between those two words is exactly the space in which the Silurian hypothesis lives, quiet and patient, waiting for someone to look more closely at the fever recorded in the stone, and to ask whether the earth was burning on its own, or whether someone, struck the match. But 56 million years, as vast as it seems, is not the deepest chamber in the archive of catastrophe. There are older silences, older scars, older extinctions so total and so violent that they dwarf the PETM, the way an ocean dwarfs a puddle. And the greatest of these, the one that nearly ended the experiment of complex life on this planet altogether, left behind a wound in the geological record so deep that even now, 250 million years later, scientists are still arguing about what exactly delivered the blow. 252 million years ago, something happened to the Earth that was so catastrophic, so overwhelmingly destructive that it nearly sterilized the planet entirely. It is called the Permian-Triassic extinction, and among paleontologists it carries a name that requires no elaboration: the Great Dying. It was not the most famous mass extinction. That distinction belongs to the asteroid impact that ended the age of the dinosaurs 66 million years ago, an event so dramatic and so cinematically compelling that it has become part of popular mythology. But the Great Dying was worse. It was not just worse, it was worse by a margin so vast that comparison becomes almost meaningless. 96% of all marine species vanished. 70% of terrestrial vertebrate species disappeared. Entire orders of insects, creatures so resilient, so adaptable, so capable of surviving almost anything the planet can throw at them, were annihilated. Forests collapsed on a global scale, replaced by fungal blooms so extensive that their spores dominate the fossil record for millions of years afterward. A world of decay where the machinery of decomposition overwhelmed the machinery of growth. The oceans became stratified. Anoxia poisoned vast dead zones where hydrogen sulfide rose from the deep and turned the shallow waters toxic. Some researchers have suggested that the hydrogen sulfide reached the atmosphere itself, destroying the ozone layer and bathing the land in lethal ultraviolet radiation. The sky, if this hypothesis is correct, would have turned a sickly green. The conventional explanation for this apocalypse centers on the Siberian Traps, one of the largest volcanic events in Earth's history. Over a period of roughly 1 million years, enormous volumes of basaltic lava erupted across what is now Siberia, covering an area approximately the size of Western Europe. The eruptions released staggering quantities of carbon dioxide, sulfur dioxide, and other gases, triggering a cascade of environmental disasters: global warming, ocean acidification, ozone depletion, acid rain. The Siberian Traps hypothesis is well supported by geochronological data that places the eruptions in close temporal proximity to the extinction boundary. It is the dominant model. It is taught in textbooks, and it is, in broad outline, almost certainly part of the truth. But the details resist simplicity. The Great Dying did not proceed as a single smooth wave of destruction. The extinction appears to have unfolded in multiple pulses, separated by intervals of partial recovery. Some researchers have identified at least 2 distinct phases: an initial crisis followed by a second, possibly more severe collapse, suggesting that the killing mechanisms were not continuous but episodic, as if the planet were being struck repeatedly rather than subjected to a single sustained assault. The precise sequence of events, their relative timing, and their causal relationships remain subjects of active debate in the scientific literature, with new studies regularly revising the timeline and the hierarchy of kill mechanisms. What is particularly striking is the sheer multiplicity of the destruction. The Great Dying was not caused by one thing. It appears to have been caused by everything simultaneously: warming, acidification, anoxia, toxic gas release, ozone destruction. Each of these mechanisms has been documented in the geological record, and each is individually capable of causing significant biological stress. But all of them occurring together in the same narrow window of geological time creates a convergence that some scientists have described as suspiciously comprehensive. The word suspiciously is not used lightly in scientific discourse. It reflects a genuine unease, not a conspiracy theory, but an acknowledgement that the completeness of the destruction, the precision with which every major environmental system was simultaneously destabilized, exceeds what straightforward volcanic outgassing would be expected to produce. Gregory Retalak, a geologist at the University of Oregon, has spent decades studying the Permian-Triassic boundary and has published extensively on anomalies that do not fit neatly into the volcanic model. His work on paleosols, ancient soil profiles preserved in the rock record, has revealed patterns of environmental disruption that are difficult to reconcile with a purely volcanic cause. He has documented evidence of rapid atmospheric change, sudden shifts in soil chemistry, and patterns of ecological collapse that suggest something more abrupt and more localized than the slow, diffuse outgassing of a continental flood basalt province. His interpretations remain controversial, and many of his colleagues disagree with his conclusions. But the data he has collected is real, and it adds to a growing body of evidence suggesting that the standard model, while fundamentally correct in identifying volcanism as the primary driver, may be incomplete. Other researchers have explored the possibility that the Siberian Trap's eruptions were themselves triggered or amplified by an impact event, an asteroid or comet strike that destabilized the crust and initiated the volcanic catastrophe. The evidence for such an impact is ambiguous. Some studies have reported anomalous concentrations of iridium and other platinum group elements at the Permian-Triassic boundary, similar to the iridium anomaly that provided the smoking gun for the Chicxulub impact at the end of the Cretaceous. Others have found fullerenes, unusual carbon molecules, containing trapped noble gases with isotopic ratios suggestive of an extraterrestrial source. But these findings have not been universally replicated, and the debate continues. What the Silurian Hypothesis adds to this conversation is not a new explanation for the Great Dying. It adds a new category of explanation, one that has never been formally considered. If a technological civilization existed in the late Permian, a civilization that had developed the capacity to alter its environment on a large scale, the collapse of that civilization, or the consequences of its industrial activity, could, in principle, produce exactly the kind of multi-system environmental catastrophe observed at the Permian-Triassic boundary. The carbon release, the warming, the acidification, the ozone depletion, these are not merely the signatures of volcanism. They are also the projected consequences of unchecked industrial activity, extrapolated over millennia. This is not to say that the Great Dying was caused by an ancient civilization. The volcanic explanation is supported by substantial evidence, and no direct evidence of a Permian technological species has ever been found. But the point, once again, is methodological rather than evidential. No one has looked. No one has examined the Permian-Triassic boundary sediments for synthetic molecules, for transuranic elements, for the specific chemical fingerprints that would distinguish industrial activity from volcanic outgassing. The analytical techniques exist. The question has simply never been asked, because the question within the current framework of geological science is unthinkable. And there is something else. Something that sits at the edge of the data, not quite in focus, not quite resolvable with current methods. The Permian world in the millions of years before the extinction was a world of remarkable biological complexity. The synapsids, the lineage that would eventually give rise to mammals, had already produced species of considerable size, behavioral sophistication, and ecological diversity. Some, like the cynodonts, had developed features that we associate with advanced mammalian life: differentiated teeth, upright posture, possible endothermy, complex jaw mechanics that suggest a capacity for varied and perhaps selective feeding. The late Permian was not a world of simple creatures, it was a world of elaboration, of increasing specialization, of evolutionary experiments that were reaching towards something, though what that something might have been, we cannot say, because the Great Dying ended the experiment before its results could be read. The destruction was so complete that it reset the trajectory of life on Earth. The lineages that survived were not the most complex, they were the most resilient, small, generalized, capable of enduring extreme conditions. The elaborate biological architectures of the late Permian were swept away, and the world that emerged from the ashes was simpler, emptier, and profoundly different. It took 10 million years for ecosystems to recover even a fraction of their former diversity. The Great Dying was not just an extinction, it was an amputation of possibility, a severing of evolutionary pathways that can never be retraced. And so the question lingers, not as assertion, but as absence. If the Permian world had been given another 10 million years, another 50 million, without the interruption of the Great Dying, what might it have produced? What cognitive capacities were developing in those increasingly complex synapsid brains? What behaviours were emerging that the fossil record with its brutal selectivity cannot capture? And when the fire came, when the sky turned green and the oceans turned to poison and 96% of everything alive was erased, what exactly was lost? Not just species, not just ecosystems, but possibilities, trajectories, the seeds of something that might, given time, have learned to wonder about its own existence. The Earth does not mourn what it destroys, it simply begins again with whatever fragments remain, but the fragments do not remember what came before them, and neither, it seems, do we. The Great Dying closed a door so thoroughly that we cannot even see where it once stood. What lies behind it? What world? What minds? What questions asked and answered in a language of chemistry and bone? Remain sealed in a darkness so old and so deep that even the rocks have forgotten how to speak of it. But there is another darkness, older still, more fundamental, that operates not through catastrophe but through patience. It does not destroy in a single blow. It consumes slowly, continuously, atom by atom, plate by plate, over spans of time that make even the Great Dying look like a momentary interruption. And it is to this deeper engine of forgetting that the story must now turn. The engine has no name in ordinary language, because ordinary language was not built to describe something so slow, so vast, and so utterly indifferent to everything that lives upon its surface. It is the process by which the Earth consumes itself and remakes itself endlessly, without pause and without memory. It is the reason that the planet beneath our feet is not the same planet that existed 100 million years ago, not merely in the sense that its climate has changed or its species have turned over, but in the most literal physical sense. The rock itself is different. The ground on which we stand is not ancient, it is recycled, and the machinery that recycles it operates on a scale and at a pace that renders even the most durable artifacts of any civilization, real or hypothetical, ultimately, inevitably impermanent. The discovery of this machinery is one of the great intellectual achievements of human history, and like many such achievements, it began not with a sudden revelation, but with a slow, almost reluctant recognition that the world was far stranger and far older than anyone had previously imagined. In the late 18th century, a Scottish farmer and gentleman scientist named James Hutton stood on the coast of Berwickshire at a place called Sicker Point and looked at something that should not have been possible. The rocks before him were arranged in two distinct layers. The lower layer consisted of vertical slabs of grey greywacke, ancient marine sediments tilted on their side by some immense and forgotten force. The upper layer was composed of horizontal beds of red sandstone, laid down calmly and evenly atop the tortured remains of what had come before. Between the two layers there was a boundary, a surface called an unconformity, that represented not a moment but an abyss. An unimaginable span of time in which the lower rocks had been deposited, compressed, uplifted, tilted, eroded to near flatness, and then submerged again beneath a new sea that deposited the upper layer as if nothing had happened. Hutton understood what he was seeing, and it shook him. His companion, the mathematician John Playfair, later wrote that at Sicker Point the mind seemed to grow giddy, looking so far into the abyss of time. Hutton had glimpsed what no one before him had fully grasped, that the Earth was not thousands of years old as the biblical chronology suggested, but inconceivably ancient, and more than ancient, cyclical. The planet was not a static stage on which the drama of life played out. It was a machine constantly building and destroying, raising mountains and grinding them to sand, opening oceans and closing them again, in cycles so long that human history occupied less than a single revolution of the wheel. What Hutton intuited, the 20th century confirmed with devastating precision. The theory of plate tectonics, which emerged in the 1960s from the convergence of seismology, paleomagnetism, and ocean floor mapping, revealed that the Earth's surface is divided into roughly 15 major plates of rigid lithosphere, floating on a subconvecting layer of hot ductile rock called the asthenosphere. These plates move, typically at rates of a few centimetres per year, roughly the speed at which fingernails grow. But over millions of years, those centimetres accumulate into thousands of kilometres. Continents drift, collide, fragment and reassemble in configurations that bear no resemblance to the world we know. The Atlantic Ocean did not exist 200 million years ago. The Himalayas did not exist 50 million years ago. The Mediterranean is the remnant of a once vast ocean called Tethys, which has been slowly crushed out of existence by the northward advance of Africa into Europe. But plate tectonics does not merely rearrange the surface, it destroys it. At convergent boundaries where plates collide, one plate is forced beneath the other in a process called subduction. The descending plate plunges into the mantle, carrying with it everything on its surface: sediment, rock, fossils, whatever traces of the past it might have held. The subducted material is heated, compressed, and eventually reabsorbed into the mantle's convective flow, melted and mixed and recycled into new rock that will eventually rise again at a mid-ocean ridge or a volcanic arc, carrying no memory of what it once was. This is not a gentle process. It is geological cremation, and it is happening continuously at every subduction zone on the planet, consuming oceanic crust at a rate of several square kilometres per year. The consequence of this process is stark and absolute. No oceanic crust on Earth today is older than approximately 200 million years. Everything older has been subducted. The ocean floors, which cover more than 60% of the planet's surface, are a blank slate, geologically speaking. They contain no record of anything that happened before the Jurassic period. The Permian ocean floor is gone. The Carboniferous ocean floor is gone. The Devonian, the Silurian, the Ordovician, all consumed, all recycled, all returned to the undifferentiated magma from which they came. If a civilization had existed on a continental shelf 400 million years ago, or on a volcanic island chain 300 million years ago, the physical evidence, the ground on which it stood, no longer exists. It has been eaten by the planet. Continental crust is more durable, but it is not immune. Continents are not subducted in the way oceanic crust is. They are too buoyant, too thick, too light to be dragged into the mantle. But they are reworked. They are folded, faulted, uplifted, eroded, buried beneath kilometres of younger sediment, and metamorphosed by heat and pressure until the original minerals are recrystallized beyond recognition. A sedimentary rock containing the chemical signature of a prior civilization could be transformed by regional metamorphism into a gneiss or a schist, its original chemistry scrambled, its isotopic ratios reset, its story overwritten by the brute thermodynamic processes of the deep crust. The Earth does not merely lose information, it actively rewrites it, replacing old narratives with new mineral assemblages that bear no trace of what came before. This is the Great Eraser. Not a single catastrophic event, but a continuous subshi, patient planetary-scale process of destruction and renewal that has been operating for 4.5 billion years. And its implications for the Silurian hypothesis are profound. because it means that the absence of evidence for a prior civilization is not merely a function of the rarity of fossilization or the fragility of artifacts. It is a function of the Earth's fundamental geology. The planet is not a passive archive, it is an active destroyer of its own past. And the further back in time one looks, the more completely the destruction has been accomplished. Schmidt and Frank acknowledged this directly in their paper. They noted that the chances of detecting a prior industrial civilization decrease dramatically with age, not because such a civilization is less likely to have existed, but because the geological processes that would preserve its traces become increasingly hostile. For a civilization that existed in the Cenozoic, the last 66 million years, some hope of detection remains, particularly in deep ocean sediment cores that have escaped subduction. For a civilization in the Mesozoic, the prospects are dimmer. For a civilization in the Paleozoic or earlier, the chances approach zero, not because the question is absurd, but because the evidence would have been systematically destroyed by the very planet on which it arose. There is something almost theological about this realization. The Earth, in its blind mechanical processes, behaves like a deity that creates and destroys worlds without awareness or intention. It raises continents and grinds them to dust. It opens oceans and swallows them whole. It buries the dead and then melts their graves. And through it all, it keeps no permanent record, acknowledges no history, preserves no memory except by accident. The rare, improbable accident of a fossil, a chemical trace, a thin anomalous layer in a core sample that happened to survive the relentless grinding of the planetary machine. Hutton, standing at Sicker Point, famously declared that he could see no vestige of a beginning and no prospect of an end. He meant it as a statement about the Earth's age, its incomprehensible cyclic antiquity. But the phrase carries a second meaning, one that Hutton himself could not have intended. If there is no vestige of a beginning, then there is no vestige of anything that came before us either. The Earth has no obligation to remember. It has no capacity to remember. It simply turns and turns and turns, folding everything it has ever known back into itself, leaving behind only the thinnest, most fragmentary, most accidental traces of the worlds it has already consumed. And yet, and this is the paradox that sustains the inquiry, some traces do survive, not many, not reliably, not in ways that are easy to read or impossible to misinterpret, but some. Anomalies in the chemical record, unexplained spikes in isotopic data, objects found in strata where they should not be, catalogued and then quietly shelved because they do not fit the framework, because they challenge assumptions that no one is prepared to revisit. It is to these anomalies, these stubborn, uncomfortable fragments of the unexamined past, that the inquiry now must turn carefully, skeptically, but with eyes open to the possibility that the margins of what we know may contain more truth than the centre. The margins of what we know have always been inhabited by uncomfortable things, objects, observations, measurements that do not fit the framework, that resist classification, that sit in the space between the explained and the inexplicable like stones in a shoe. Science, at its best, treats these anomalies as invitations, signals that the current model is incomplete, that something has been missed, that the map does not yet match the territory. But science is practiced by human beings, and human beings have a complicated relationship with the things that do not fit. Sometimes the anomaly is investigated and the model is revised. Sometimes the anomaly is investigated and found to be an error. And sometimes, more often than the official narrative admits, the anomaly is simply set aside, catalogued without explanation, filed in the back of a drawer where it will not disturb the orderly arrangement of what is already known. The history of archaeology and geology is littered with such objects. They are sometimes called OOP arts, out-of-place artifacts, a term coined not by mainstream science, but by the American naturalist Ivan T. Sanderson in the mid-20th century. The label itself carries a faint odour of disrepute, associating these finds with the fringes of pseudoscience and conspiracy theory. And many of the objects that have been claimed as OOP arts are, upon investigation, exactly what skeptics say they are: misidentified natural formations, products of known but unusual geological processes, hoaxes, or simply artifacts whose dating has been misunderstood. The field is cluttered with noise, and the noise has made it easy, perhaps too easy, to dismiss the signal. But not all of the anomalies dissolve under scrutiny. Some remain stubbornly, irreducibly strange, resisting both the explanations of true believers and the dismissals of committed skeptics. They do not prove anything. They do not confirm the Silurian hypothesis or any other grand theory. But they occupy a space that honest inquiry cannot entirely ignore, the space of the genuinely unexplained. Consider the Klerksdorp spheres. These are small, roughly spherical objects, typically 1 to 10 centimeters in diameter, found in pyrophyllite deposits near the town of Ottosdal in South Africa. The deposits are approximately 2.8 billion years old, Precambrian, from an era when the most complex life on Earth consisted of single-celled organisms and microbial mats. The spheres are composed of various minerals, primarily hematite and wollastonite, and many of them exhibit features that have attracted persistent attention. Grooves or ridges that run around their circumference, internal radial structures, and a degree of symmetry that some observers have found difficult to attribute to purely natural processes. In the 1980s, a museum curator named Rolf Marx stated publicly that the spheres were so perfectly balanced and so finely grooved that they appeared to be manufactured, and that one of them, placed under a glass case, had been observed to rotate on its own axis, a claim that added a layer of mystery or mysticism depending on one's disposition. The mainstream geological explanation is that the Klerksdorp spheres are concretions, natural mineral formations that develop through the precipitation of minerals from groundwater within a sedimentary matrix. Concretions are common in the geological record and can take on a wide variety of shapes, including spheres, discs, and ovoids. The grooves, according to this explanation, are the result of differential weathering along internal structural planes. The explanation is plausible, well supported by analogues from other geological settings, and accepted by the overwhelming majority of geologists who have examined the objects. And yet the explanation has not silenced the questions entirely, because plausible is not the same as proven, and because the specific combination of features exhibited by some of the Klerksdorp spheres, the symmetry, the regularity of the grooves, the internal radial structure, remains, in the precise language of the geological literature, unusual. The Klerksdorp spheres are 2.8 billion years old. At that depth of time, the Silurian hypothesis becomes almost untestable. The geological recycling discussed earlier would have obliterated virtually any conceivable trace of technology. The spheres are almost certainly natural, but they are a reminder of how easily the categories of natural and artificial blur at the margins, and how much our interpretation of an object depends on the framework we bring to it. If the same objects were found in a stratum 10,000 years old, in association with other artifacts, they would be examined with entirely different eyes. Far more recent and far more genuinely puzzling is the Antikythera mechanism, though its puzzlement operates in a different register. Recovered in 1901 from a Roman-era shipwreck off the coast of the Greek island of Antikythera, this corroded bronze device, roughly the size of a shoebox, was initially dismissed as an uninterpretable lump of oxidized metal. It was not until decades later, through a series of increasingly sophisticated analyses, including X-ray tomography performed in the early 2000s, that the true nature of the object was revealed. It was a mechanical computer, an analog calculating device of extraordinary sophistication, containing at least 30 interlocking bronze gears capable of predicting eclipses, tracking the cycles of the moon, modelling the movements of the 5 known planets, and even calculating the dates of the ancient Olympic Games. The Antikythera mechanism dates to approximately the 2nd century before the Common Era, and nothing remotely comparable in mechanical complexity appears in the historical record for another 1400 years. It is, in the most literal sense, an artifact out of time, not because it was placed there by time travellers or ancient aliens, but because it represents a level of technological achievement that surrounding civilization apparently did not sustain or replicate. The knowledge required to build it, the understanding of gear theory, astronomical cycles, and precision and metalwork existed, was applied, and then was lost. The mechanism is not evidence of a prehistoric civilization. It is something perhaps more unsettling, evidence that knowledge, even within recorded history, can appear, flourish briefly, and vanish so completely that its very existence becomes a source of disbelief when it is finally rediscovered. If knowledge can be lost within the span of a few centuries, within a civilization that left behind vast libraries and entire cities of stone, what might be lost across millions of years, across extinction events, across the grinding recycling of the planet's own crust? The Antikythera mechanism survived only because it sank to the bottom of the sea, sealed in anaerobic conditions that slowed its corrosion to a fraction of what it would have been on land. It was an accident of preservation so improbable that if the shipwreck had settled a few hundred meters deeper, or in warmer waters, or in sediment with different chemistry, the mechanism would have dissolved into nothing, and we would never have known that such a device had been conceived, let alone built. There is also the Dorchester pot, a small metallic vessel reportedly found in 1852 during blasting operations in a rock formation near Dorchester, Massachusetts. According to an account published in Scientific American in June of that year, the vessel was extracted from solid pudding stone, a conglomerate rock estimated to be of Precambrian age. The pot was described as bell-shaped, approximately 4.5 inches high, with inlaid silver floral designs. If the account is accurate, it would place a manufactured metallic object inside a rock formation hundreds of millions of years old, a finding so radical that it would overturn virtually every assumption about the history of intelligence on Earth. The problem, of course, is that the account cannot be verified. The original object has been lost. The geological context was destroyed by the blasting, and the standards of documentation in 1852 were not what they are today. The Dorchester pot may be a genuine anomaly. It may be a misidentification. It may be a hoax. It exists in a twilight zone of incomplete evidence, where certainty is impossible in either direction. And this is the fundamental problem with anomalous artifacts. They are almost by definition poorly documented. The very qualities that make them extraordinary, their apparent impossibility, their contradiction of established frameworks, are the same qualities that invite skepticism, mishandling and dismissal. Objects that challenge the paradigm are held to a higher standard of evidence than objects that confirm it, which is scientifically appropriate, but creates an asymmetry in which the anomalous is always more likely to be discarded than the expected. The sociology of knowledge works against the outlier. The institution protects the framework, and the framework, in the case of the deep past, includes the invisible assumption that intelligence is new, and that the Earth before humanity was a world without minds. What the anomalies demand is not belief. They demand a more honest accounting of what we do not know. They demand the acknowledgement that the categories of natural and artificial are not always as clear as we pretend, especially at the extremes of time. They demand the recognition that the absence of evidence, in a record as fragmentary and biased and actively self-destroying as the geological record, is a very different thing from the evidence of absence. And they demand, quietly, insistently, from the dusty margins of museum collections and the footnotes of geological surveys, that someone, somewhere take the time to look again, with fresh eyes and fewer assumptions, at the things that do not fit, because it is in the things that do not fit that the next question always hides. And the next question in the long journey of the Silurian Hypothesis is not about objects at all. It is about minds. Not human minds, but the broader question of whether intelligence itself, the capacity to observe, to manipulate, to wonder, is as rare in the history of this planet as we have assumed, or whether it is something that the machinery of evolution produces again and again, in different forms, in different eras, each time forgetting the last. Whether the machinery of evolution produces minds again and again, this is not a fringe question. It is one of the deepest and most contested questions in modern biology, and its answer has implications that reach far beyond the confines of any single hypothesis about ancient civilizations. It touches the very nature of what intelligence is, how it arises, whether it is a fluke or a tendency, an accident or an inevitability. And the evidence, when examined without the comfort of familiar assumptions, is far more ambiguous than the standard narrative suggests. The standard narrative goes something like this: intelligence, at least of the kind capable of producing technology, language, and civilization, evolved exactly once in the history of life on Earth. It appeared in the genus Homo within the last few million years, and it reached its full flowering in Homo sapiens roughly 300,000 years ago. This is treated not as a hypothesis but as a fact, a cornerstone of biological anthropology, reinforced by decades of research into human evolution, cognitive neuroscience and comparative psychology. And in a narrow technical sense, it is true. No other species currently on Earth has built cities, written books, or split the atom. The gap between human cognitive capacity and that of any other living species is, by any measure, enormous. But the conclusion drawn from this observation, that intelligence of a high order is vanishingly rare, a once-in-a-planetary lifetime occurrence, rests on a logical error so fundamental that it's remarkable how seldom it is examined. The error is this: we are drawing conclusions about the probability of an event by observing a sample size of one. We have one planet, one biosphere, one evolutionary history to examine, and within that history, we are observing the outcome at a single moment in time, the present, and extrapolating from that snapshot to the entire 4.5 billion year span of life on Earth. It is as if someone opened a novel to a random page, found only one character speaking, and concluded that the book contained only one voice. The phenomenon of convergent evolution should give us pause before accepting so sweeping a conclusion. Convergent evolution occurs when unrelated lineages independently develop similar structures, behaviors, or capabilities in response to similar environmental pressures. It is not a rare phenomenon. It is ubiquitous. The eye has evolved independently at least 40 times across the animal kingdom. Invertebrates, mollusks, arthropods, cnidarians, and others, each time arriving at a similar solution to the same fundamental problem of converting light into information. Flight has evolved independently at least 4 times in vertebrates alone. In pterosaurs, birds, bats, and, arguably, in certain gliding reptiles and mammals. Echolocation has evolved independently in bats and dolphins. Warm-bloodedness has evolved independently in mammals and birds, and possibly in some lineages of dinosaurs and even certain fish. The list is extensive and growing, and its message is clear. When evolution encounters a problem that can be solved, it solves it, often multiple times, in multiple lineages, using different raw materials but arriving at a functionally equivalent results. The question then is whether intelligence, the capacity for abstract reasoning, tool use, social learning, and environmental manipulation, is the kind of trait that convergent evolution would produce repeatedly, or whether it is genuinely unique, a one-off invention so improbable that it required a specific and unrepeatable sequence of evolutionary circumstances. The evidence from the living world suggests that the answer is far closer to the former than the latter. Consider the octopus. The common octopus, Octopus vulgaris, and its relatives in the cephalopod family possess cognitive abilities that are, by any objective measure, extraordinary. They can solve complex mazes, open childproof containers, recognize individual human faces, use tools, and engage in what appears to be play, a behavior that in vertebrates is considered a hallmark of advanced cognition. Their nervous system is radically different from that of any vertebrate, distributed across 8 semi-autonomous arms, with roughly 2/3 of their neurons located outside the central brain. They diverge from the vertebrate lineage over 500 million years ago, meaning that any cognitive sophistication they possess evolved entirely independently. The octopus is not a distant cousin of human intelligence. It is a separate invention, arrived at by a completely different evolutionary pathway in an entirely different body plan, in a world of water rather than air. Or consider the corvids, crows, ravens, jays and their relatives. These birds possess brains that are anatomically nothing like the mammalian neocortex, yet they exhibit cognitive abilities that rival those of great apes. New Caledonian crows manufacture tools from materials they find in their environment, stripping leaves to create hooked probes, bending wire to retrieve food from containers, and passing tool-making techniques from one generation to the next through social learning. Ravens engage in what cognitive scientists call tactical deception, hiding food, then pretending to hide it elsewhere when they suspect they are being watched. Eurasian magpies pass the mirror test, a standard measure of self-recognition that most mammals fail. These are not instinctive behaviors encoded in fixed neural circuits. They are flexible, innovative, context-dependent responses to novel problems, the hallmarks of what in any other context we would simply call intelligence. And then there are the cetaceans. Dolphins and whales possess the largest and most complex brains of any animals on Earth, with neocortical surface areas that in some species exceed those of humans. Bottlenose dolphins use signature whistles that function as individual names, a capacity for symbolic labeling that was once thought to be uniquely human. Orcas live in matrilineal societies with distinct cultural traditions, specific hunting techniques, vocal dialects, and social behaviors that are transmitted across generations and that differ from one pod to another, even among populations living in the same waters. Sperm whales produce patterns of clicks, called codas, that vary by clan, in ways that linguists have compared to the structural features of human language. Though the comparison remains controversial and unresolved, what all of these examples demonstrate is not that octopuses, or crows or dolphins are as intelligent as humans. They are not, at least not in the specific dimensions of intelligence that humans value: abstract mathematics, written language, cumulative technology. But they demonstrate something that may be more important for the question at hand, that the evolutionary pressure toward cognitive complexity is not unique to the primate lineage. It has appeared independently in multiple phyla, in multiple ecological contexts across hundreds of millions of years of evolutionary time. Intelligence, in some form, is not an aberration. It is a recurring theme in the story of life on Earth. This is where the economist Robin Hanson's concept of the Great Filter becomes relevant. Though Hanson formulated it in the context of the Fermi paradox, the question of why, if the universe is so vast and so old, we have not yet detected evidence of extraterrestrial civilizations. Hanson proposed that somewhere in the sequence of steps from simple chemistry to spacefaring civilization, there must be one or more extremely improbable transitions, filters, that prevent most lineages from reaching the endpoint. The question is where the filter lies. Is it in the origin of life itself? In the emergence of eukaryotic cells? In the evolution of multicellularity? Or is it later, in the development of intelligence? Or in the survival of technological civilizations once they arise? If the filter is early, if the hard part is getting from chemistry to biology or from prokaryotes to eukaryotes, then intelligence may be relatively easy to evolve given enough time and the right conditions. And if intelligence is relatively easy to evolve, then it becomes increasingly difficult to maintain the assumption that it evolved only once on a planet that has been habitable for nearly 4 billion years. The convergent evidence from octopuses, corvids, and cetaceans suggests that the pressure toward complex cognition is strong, widespread, and not dependent on any single body plan or neural architecture. If this pressure has produced near intelligence in multiple lineages within the last few 100 million years, what might it have produced in the billions of years before that, in worlds we have no record of, in ecosystems that have been subducted into the mantle, in eras so remote that even the chemistry of the atmosphere was unrecognisably different? The honest answer is that we do not know. We cannot know given the current state of the evidence, but the question is no longer whether intelligence could have arisen before. The question is whether the conditions that produce it, environmental complexity, competitive pressure, the availability of energy-rich food sources, the advantages of social cooperation are rare or common in the long history of life on this planet, and everything we have learned about convergent evolution suggests that these conditions are not rare at all. They are the default state of any sufficiently complex biosphere. Intelligence may not be a miracle, it may be a pattern, one that the Earth has woven before, perhaps many times, in threads so old and so thoroughly unravelled that only the faintest trace of the pattern remains, if it remains at all. And if intelligence is a pattern rather than a miracle, then the question shifts again. It moves from biology to geology, from the living world to the dead rock, from the question of whether minds could have existed to the question of whether their passing would have left a mark, any mark, in the deep record of the planet. A mark not in the shape of a skull or a tool, but in the shape of a molecule, an isotope, a faint and ambiguous signal in a stratum of ancient stone. The kind of mark that Schmidt and Frank proposed to look for. The kind of mark that no one has yet looked for with sufficient care. And among the ancient eras that might harbour such a mark, there is one that stands out, not because it is the most likely candidate, but because it is the most tantalising. A period of Earth's history so rich in energy, so extravagant in biological complexity, so lush and so strange that it built the very fuel on which our own civilization now depends. The fuel that powers the modern world was not always fuel, it was once alive, towering, breathing, photosynthesizing, reaching toward a sky that held more oxygen than any atmosphere before or since. The Carboniferous period, stretching from approximately 359 to 299 million years ago, was an era of such staggering biological productivity that its residue, compressed and transformed by millions of years of heat and pressure, became the coal deposits that would ignite the Industrial Revolution and reshape human civilization. We burn the Carboniferous every day. We heat our homes with it, generate our electricity from it, forge our steel with it. But we rarely pause to consider what kind of world produced it, and whether that world in its extraordinary complexity and abundance might have produced something more than forests. The Carboniferous Earth was almost unrecognisably different from the planet we inhabit. The continents were converging toward the supercontinent Pangaea, but the process was incomplete. Vast shallow seas flooded the interiors of land masses, creating enormous coastal swamps and wetlands that stretched across what are now North America, Europe, and China. These swamps were dominated by trees unlike any that exist today. Lepidodendron, the scale tree, grew to heights of 40 metres or more, its trunk covered in distinctive diamond-shaped leaf scars that fossilise with eerie regularity. Sigillaria, the seal tree, stood in dense groves along the edges of waterways. Calamites, giant horsetails, rose 10 to 20 metres into the air. These were not the trees of a modern forest. They were something older, stranger, and in many ways more extravagant vascular plants that had discovered the structural possibilities of lignin and cellulose, and were exploiting them with an exuberance that had never been seen before and would never be quite replicated. And here is the detail that transforms the Carboniferous from a chapter in Earth history into something resembling a parable. The trees of the Carboniferous produced vast quantities of lignin, the complex polymer that gives wood its rigidity, its strength, its resistance to compression. But the microorganisms capable of breaking down lignin, the white rot fungi and their enzymatic machinery, had not yet fully evolved. The result was a world in which dead trees did not rot. They fell, they accumulated, they were buried by some sediment and by subsequent generations of their own kind, layer upon layer upon layer, building up deposits of organic matter hundreds of meters thick in some locations. These deposits, subjected to geological pressure and heat over millions of years, became coal. The Carboniferous did not merely produce forests, it produced forests that could not be consumed by the very biosphere that grew them, and so they were preserved, entombed in the earth, waiting for a species that would not appear for another 300 million years to dig them up and set them on fire. The atmosphere of the Carboniferous reflected this extraordinary productivity. Oxygen levels are estimated to have reached 35%, compared to approximately 21% today. The implications of this hyperoxygenated atmosphere were dramatic. Fire was more easily ignited, and wildfire evidence is abundant in the Carboniferous fossil record. But more strikingly, the elevated oxygen levels permitted the evolution of terrestrial arthropods of enormous size. Meganeura, a dragonfly relative, had a wingspan of approximately 75 centimeters. Arthropleura, a millipede-like creature, reached lengths of over 2 meters, the largest known land invertebrate in the history of the planet. These were not anomalies. They were products of an atmosphere that allowed respiratory systems, particularly the passive tracheal systems of arthropods, to support body sizes far beyond anything possible at modern oxygen levels. But the Carboniferous was not only a world of giant insects and unrotting trees, it was also a world in which vertebrate life was undergoing a profound transformation. The first amniotes, vertebrates capable of reproducing on land without returning to water, appeared during the Carboniferous, a development as significant in its way as the origin of photosynthesis or the evolution of multicellularity. Among these early amniotes were the ancestors of every reptile, every bird, and every mammal that would ever live. The evolutionary experiments of the Carboniferous laid the groundwork for everything that followed: the dinosaurs, the mammals, the primates, and ultimately the species now asking whether something intelligent might have preceded it. The cognitive capacities of Carboniferous organisms are, of course, unknown. The fossil record preserves bones, teeth, and occasionally soft tissue impressions, but it does not preserve behavior, and it certainly does not preserve thought. What can be said is that the Carboniferous biosphere was a system of extraordinary energy abundance and ecological complexity, precisely the conditions that in every other context we know of drive the evolution of increasingly sophisticated organismal responses. Predation pressures were intense. Competition for resources was fierce. The ecological niches were multiplying rapidly as life colonized new environments and developed new strategies for survival. These are the conditions that select for neural complexity, for behavioral flexibility, for the capacity to learn and adapt rather than simply react. None of this constitutes evidence that intelligence evolved in the Carboniferous. The fossil record of the period, while rich in plant material and arthropod remains, is comparatively sparse when it comes to terrestrial vertebrates, particularly small-bodied species that might have occupied ecological niches favourable to cognitive development. The biases of preservation, the preference for swamp environments, the underrepresentation of upland and dryland faunas mean that entire communities of organisms may have existed without leaving any trace. This is not speculation. It is a well-recognized limitation of Carboniferous paleontology, acknowledged in the technical literature and lamented by researchers who study the period. What the Carboniferous does offer to the Silurian hypothesis is not evidence but context, a demonstration that the conditions for complex life, for energy-rich ecosystems, for evolutionary pressure toward cognitive sophistication have existed on this planet for hundreds of millions of years. The Carboniferous was not a barren world waiting for intelligence to be invented in the distant future. It was a world of almost reckless biological exuberance, a world so productive that it literally built the energy reserves that another civilization, hundreds of millions of years later, would depend upon for its own survival. And there is an irony embedded in this relationship that borders on the philosophical. We burn the Carboniferous to power our cities, our factories, our vehicles, our digital infrastructure. Every lump of coal, every molecule of natural gas derived from Carboniferous deposits is a fragment of that ancient world, a piece of compressed sunlight captured by a tree that grew 300 million years ago in a swamp that no longer exists on a continent that has since been dismembered by tectonic forces. We are, in a very real sense, living on the corpse of the Carboniferous. Our civilization is a parasite on a dead world, extracting energy from the remains of an ecosystem that flourished and perished long before anything resembling a human being existed. But here's the thought that refuses to settle, that circles back again and again like a bird unable to find a place to land. We have never asked whether something in that world might have done the same. Not at our scale, not with our technology, not with our global reach, but in some smaller, more localized way. A species that discovered fire in an atmosphere already primed for combustion. A species that learned to use the abundant organic material around it for purposes beyond simple consumption. A species that in the long millennia of the Carboniferous's extraordinary energy surplus developed capacities that the fossil record, blind to behavior, deaf to thought, indifferent to intention, simply cannot capture. This is not a claim, it is an observation about the limits of what we can exclude. The Carboniferous lasted 60 million years. That is longer than the entire Cenozoic era, the age of mammals, the age that includes us. In 60 million years, at modern rates of evolution, entire families of organisms can arise, diversify, and go extinct without leaving a single fossil in certain environments. The idea that we can confidently declare the Carboniferous empty of cognitive complexity, based on a fossil record dominated by swamp flora and giant arthropods, drawn from a handful of geological formations in a small number of locations, is not science. It is Seth, and the object of that faith is the assumption that we have always been examining, that intelligence is new, that it is ours, that the deep past was mindless. Perhaps it was. Perhaps the Carboniferous was nothing more than what the textbooks describe, a world of giant insects and primitive amphibians and endless silent rotting forests that never rotted. But the energy was there, the complexity was there, the time was there, and somewhere in the black seams of coal that run beneath the hills of Appalachia and the valleys of Wales and the plains of northern China, there may be a residue, not of intelligence perhaps, but of the conditions that make intelligence possible. A residue that we have been burning casually and without reverence for 250 years, never pausing to wonder whether the fire we are lighting now is an echo of a fire that was lit before, by hands or limbs or structures we cannot imagine, in a world so old that even its ashes have turned to stone. And stone, of course, is where the story always returns. Stone and fire and the sudden, violent end of possibility. Because whatever the Carboniferous might have been building, whatever slow trajectories of increasing complexity were unfolding in its forests and swamps and upland regions, the experiment did not continue uninterrupted. The Earth has a way of intervening, not gently, not gradually, but with the sudden, absolute finality of an event so catastrophic that it resets the entire trajectory of life. And the most famous of these interventions, the one that sits like a wall across the path of every evolutionary lineage that existed 66 million years ago, came not from the planet itself, but from the sky. It came from the sky at an angle of approximately 60 degrees, travelling at roughly 20 kilometers per second, a velocity so extreme that the air in front of it did not have time to move aside, but was instead compressed into a superheated plasma that arrived at the surface a fraction of a second before the object itself. The impactor was an asteroid, approximately 12 kilometers in diameter, composed of carbonaceous chondrite, ancient, carbon-rich rock that had been drifting through the solar system since its formation 4.5 billion years earlier. It struck what is now the Yucatan Peninsula of Mexico in a shallow sea, underlain by thick deposits of limestone and anhydrite, and in the space of a few seconds, it released energy equivalent to approximately 10 billion Hiroshima bombs. The resulting crater, now called Chicxulub, after the small town near its centre, is roughly 180 kilometers in diameter and 20 kilometers deep, though its original dimensions were larger before gravitational collapse reshaped its structure in the minutes following impact. These immediate effects were apocalyptic in the most literal sense of the word. The impact generated seismic waves that registered as a magnitude 11 earthquake, greater than anything the Earth has produced through its own tectonic processes. Tsunamis hundreds of meters high radiated outward from the impact site, scouring coastlines thousands of kilometers away. Molten ejecta, fragments of rock superheated to thousands of degrees, were launched on ballistic trajectories that carried them around the globe, re-entering the atmosphere as a rain of incandescent debris that heated the upper atmosphere to oven-like temperatures. Studies by researchers including David Kring and Daniel Derder have suggested that this thermal pulse was intense enough to ignite wildfires across entire continents, a planetary-scale conflagration that consumed forests and grasslands on a scale that defies comprehension. The soot and ash from these fires, combined with the fine particulate matter ejected by the impact itself, entered the stratosphere and spread across the globe, blocking sunlight for months or years. Photosynthesis collapsed, temperatures plummeted. The food chain from its base in photosynthetic organisms to its apex in the largest predators disintegrated. The extinction that followed, the Cretaceous-Paleogene event once called the Cretaceous Tertiary or KT extinction, eliminated approximately 75% of all species on Earth. The non-avian dinosaurs, which had dominated terrestrial ecosystems for over 160 million years, were annihilated. The great marine reptiles, the mosasaurs, the plesiosaurs, vanished. The ammonites, which had flourished in the world's oceans for over 300 million years, disappeared entirely. The pterosaurs, the last of the flying reptiles, were erased. What survived was, in many cases, small burrowing, generalized or aquatic, organisms capable of enduring prolonged darkness, cold, and food scarcity. The mammals that would eventually give rise to primates, and through them to humans, were among the survivors. They were at the time mostly small nocturnal insectivorous creatures, living in the ecological margins while the dinosaurs commanded the center stage. The asteroid did not create human intelligence, but it cleared the ecological space in which human intelligence would eventually become possible. This much is well established, supported by decades of research following the landmark 1980 paper by Luis and Walter Alvarez, Frank Asaro and Helen Michel, which identified the global iridium anomaly at the Cretaceous-Paleogene boundary and proposed the impact hypothesis. What is less often discussed, and what bears directly on the question of the Silurian hypothesis, is what the Chicxulub event destroyed not merely in terms of species, but in terms of cognitive potential. In the late Cretaceous, several lineages of dinosaurs have been developing traits that, in any other evolutionary context, would be recognized as precursors to advanced cognition. The most frequently cited example is Troodon, a small bipedal theropod that lived approximately 77 million years ago, toward the end of the Cretaceous. Troodon possessed one of the largest brain-to-body mass ratios of any known dinosaur, comparable to that of modern retites and approaching the range of some modern birds. Its eyes were large, forward-facing, and likely capable of binocular vision, a trait associated with depth perception and fine motor coordination. Its hands were unusually dexterous, with an opposable digit that some paleontologists have suggested could have been used for grasping and manipulation. It was almost certainly warm-blooded. It may have been feathered. And it was a social animal, with nesting behaviour that implies parental care and possibly cooperative group dynamics. In 1982, the Canadian paleontologist Dale Russell, working at the National Museum of Natural Sciences in Ottawa, published a thought experiment that took these observations to their logical, if speculative, conclusion. Russell asked, if the Cretaceous had not ended, if the asteroid had missed or had never existed, what might Troodon, or a descendant of Troodon, have become given another 66 million years of evolution? His answer was the Dinosauroid, a hypothetical bipedal creature with a large cranium, reduced snout, binocular vision, and manipulative hands, resembling in broad outline a humanoid form arrived at through a completely different evolutionary lineage. The Dinosauroid was not intended as a prediction. It was a thought experiment designed to illustrate the principle of convergent evolution and to raise the question of whether human-like intelligence might emerge from non-mammalian ancestors given sufficient time and appropriate selective pressures. Russell's Dinosauroid was controversial and remained so. Many paleontologists criticized it as too anthropocentric, too quick to assume that intelligence must converge on a human body plan. Others objected to the speculative nature of the exercise, arguing that evolutionary trajectories are too contingent, too dependent on specific environmental circumstances to be extrapolated over tens of millions of years. These criticisms have merit. Evolution is not a ladder climbing toward a human form. It's a branching tree, and the direction of any branch is shaped by local conditions, random mutations, and extinction events that are inherently unpredictable. But the criticisms, valid as they are, do not address the core of Russell's question. The question was not whether Troodon would have become a humanoid. The question was whether the cognitive trajectory that Troodon represented, the trend toward larger brains, greater dexterity, more complex social behaviour, would have continued in some form, producing something in some body plan that we would recognise as intelligent. And this question, despite the controversy surrounding the Dinosauroid, has never been convincingly answered in the negative. No one has demonstrated that the cognitive trajectory of late Cretaceous theropods was approaching a ceiling, or that the selective pressures driving brain enlargement were diminishing, or that some fundamental constraint would have prevented further cognitive development. The trajectory was real, the potential was real, and the asteroid ended both. What Chicxulub destroyed then was not merely a collection of species, it was a set of possibilities, evolutionary pathways that had been developing for millions of years and that were severed in a geological instant. The non-avian dinosaurs are often spoken of as evolutionary failures, creatures that dominated the Earth for a long time and then were wiped out by a random catastrophe. But this framing obscures what they actually were. The most successful large-bodied terrestrial vertebrates in Earth's history, a group that had survived multiple prior extinction events, diversified into an extraordinary range of ecological niches, and was, in at least some lineages, developing cognitive capacities that we are only beginning to appreciate. They did not fail, they were interrupted, and the interruption was total. The asteroid did not select for intelligence or against it. It selected for survival under conditions of prolonged environmental collapse, darkness, cold, food scarcity, acidified oceans. The traits that mattered in that crucible were not cleverness or dexterity or social complexity. They were small body size, metabolic flexibility, dietary generalism, and the ability to shelter underground or underwater. The great cognitive experiments of the late Cretaceous, whatever they were, wherever they were heading, were not tested against these criteria. They were simply erased, along with everything else that could not survive a world without sunlight. There is a tendency, in popular accounts of the Chicxulub impact, to treat it as a necessary precondition for human existence, a cosmic clearing of the stage that allowed mammals to diversify and eventually produce us. And in a narrow causal sense, this is true. Without the extinction of the non-avian dinosaurs, the ecological space for mammalian diversification would not have existed, and the evolutionary pathway to Homo sapiens would never have opened. But this framing carries a hidden assumption that deserves scrutiny. The assumption that what replaced the dinosaurs was better, or more advanced, or more significant than what came before. The mammals that diversified after Chicxulub were not inherently superior to the dinosaurs that preceded them. They were simply the survivors of a catastrophe that had nothing to do with merit and everything to do with circumstance. And this leads to a thought that is difficult to hold but impossible to dismiss. If the asteroid had arrived 10 million years later, or had never arrived at all, the cognitive trajectory of the theropod dinosaurs might have continued. Something might have emerged, something with a large brain and dexterous limbs and complex social bonds, something that looked at the stars and wondered what they were, something that might have built and burned, and left behind a thin, strange layer in the geological record that a future species, or no species at all, would one day puzzle over. The asteroid did not merely end the Mesozoic. It ended a question that had been forming solely and wordlessly in the neural architecture of creatures that would never have the chance to ask it. And in ending that question, it opened a space in which 66 million years later, a different species would arise, look back at the rubble and begin to wonder what was lost. Whether those wandering minds would ever develop the methods to detect a prior intelligence, to find its chemical ghost in the stone, to read its ectotopic signature in a core sample pulled from the ocean floor, is a question not of paleontology, but of instrumentation, of technique, of the willingness to look for something that every existing framework insists cannot be there. The willingness to look is one thing, the capacity to find is another, and the distance between the two is measured not in courage or imagination, but in methodology, in the specific, technical, often unglamorous question of what instruments to point at what samples and what signatures to search for in the resulting data. The Silurian hypothesis, whatever its philosophical implications, ultimately stands or falls on a practical question. If a technological civilization existed in Earth's deep past, what detectable traces might it have left in the geological record, and do we possess the analytical tools to identify them? Schmidt and Frank, in their 2018 paper, did not merely raise the question. They proposed answers, a taxonomy of potential technosignatures, a menu of anomalies that could in principle distinguish the residue of industrial activity from the background noise of natural geological processes. The menu is surprisingly specific, and the fact that almost none of its items have been systematically searched for is, depending on one's perspective, either a reflection of scientific prudence or a monument to institutional inertia. The most straightforward category of technosignature is synthetic chemistry, the presence of molecules that do not occur in nature and can only be produced through deliberate industrial processes. Our own civilization has generated thousands of such molecules. Chlorofluorocarbons, the compounds once widely used as refrigerants and aerosol propellants, are perhaps the most famous. They do not exist in any natural process. Their presence in the atmosphere is, definitionally, a signature of technology. Polychlorinated biphenyls, perfluoroalkyl substances, certain long-chain synthetic polymers, these too are molecules that the Earth does not produce on its own. If any of these compounds, or their degradation products, were found in a stratum of rock tens of millions of years old, the discovery would be extraordinarily difficult to explain by any natural mechanism. It would not prove the existence of a prior civilization. Science does not work in proofs, but it would constitute evidence so anomalous that it would demand a fundamental reassessment of what the deep past might contain. The challenge, of course, is persistence. Synthetic molecules are not eternal. They degrade through photolysis, hydrolysis, biodegradation, and thermal decomposition. The question is how quickly and whether any residue might survive on geological timescales. The answer depends on the specific molecule and the specific conditions of burial. Some synthetic compounds are extraordinarily resistant to degradation. Perfluorinated compounds, for example, are so chemically stable that they are sometimes called forever chemicals in the environmental science literature, a designation that, while hyperbolic on geological timescales, reflects their remarkable persistence under ordinary surface conditions. Whether such compounds could survive 50 million years of burial in sedimentary rock is an open question. It has not been tested because no one has had reason to test it. The experiment has not been designed because the hypothesis it would test has not been taken seriously enough to warrant the investment. A second category of technosignature is isotopic anomaly, specifically disturbances in the ratios of certain isotopes that would result from large-scale combustion of fossil fuels. When organic carbon is burned, the carbon dioxide released into the atmosphere carries a distinctive isotopic signature. Organic carbon is enriched in the lighter isotope, carbon-12, relative to the heavier isotope, carbon-13, a massive and rapid release of carbon-12 enriched CO2, the kind produced by burning coal, oil or natural gas, would produce a negative excursion in the carbon-13 to carbon-12 ratio recorded in marine sediments. This is precisely the kind of excursion observed at the Paleocene-Eocene Thermal Maximum, and it is precisely the kind of excursion that Schmidt and Frank identified as a potential, though not conclusive, industrial signal. The difficulty here is distinguishing between industrial and natural causes. Volcanic outgassing, the decomposition of methane clathrates, the oxidation of large organic deposits. All of these natural processes can produce negative carbon isotope excursions, and all of them have been invoked to explain the PETM and other similar events. The isotopic signature alone cannot definitively identify an industrial source, but Schmidt and Frank argued that the temporal profile of the excursion, how quickly the carbon was released, how sharply the isotopic ratio changed, and how the timing correlated with other environmental changes, might allow a more refined discrimination. An industrial release would tend to be faster and more concentrated than a volcanic one. It would correlate with specific patterns of environmental disruption, warming, acidification, biodiversity loss, in ways that might differ subtly but measurably from the patterns produced by natural carbon cycling. The analytical tools to perform this discrimination exist. They include high-resolution mass spectrometry, compound-specific isotope analysis, and advanced sedimentological techniques capable of resolving temporal events on the scale of centuries within deep-time stratigraphic records. What does not exist as yet is the institutional will to apply these tools to the specific question of prior industrial activity. A third category, and perhaps the most provocative, is the detection of transuranic elements or their decay products in ancient sediments. Transuranic elements are atoms heavier than uranium on the periodic table. With very few exceptions, trace quantities of neptunium and plutonium produced by natural nuclear reactions, such as the famous Oklo natural reactor in Gabon, transuranic elements do not occur in nature. They are produced almost exclusively by nuclear fission or neutron bombardment in artificial reactors or weapons. Plutonium-244, for example, has a half-life of approximately 80 million years. If a prior civilization had developed nuclear technology, fission reactors, nuclear weapons, or any process involving sustained nuclear chain reactions, the plutonium produced would decay over geological time, but its daughter isotopes would remain, embedded in the sedimentary record as a faint but unmistakable signature of technological activity. The Oklo reactor, mentioned above, is worth pausing on because it demonstrates that the concept of nuclear technology is not exclusively human. Approximately 2 billion years ago, in what is now the Oklo region of Gabon, West Africa, a set of natural uranium deposits achieved sustained nuclear fission, not through engineering but through a precise and improbable combination of geological and geochemical conditions. The uranium concentration was high enough, the groundwater moderation was sufficient, and the geometry of the deposits was favourable enough to sustain chain reactions that operated intermittently for hundreds of thousands of years. The Oklo reactor was discovered in 1972, when French nuclear scientists noticed anomalous depletion of uranium-235 in ore samples from the mine. The depletion was consistent with the isotopic changes produced by sustained fission, and subsequent investigation confirmed that natural nuclear reactors had operated at the site, producing measurable quantities of fission products and transuranic elements that remain detectable today, 2 billion years after the reaction ceased. Oklo proves that nuclear processes can leave detectable traces in the geological record across billions of years. It also provides a baseline, a natural nuclear signature against which an artificial one could, in principle, be compared. The distribution of fission products in a natural reactor follows predictable patterns determined by the physics of the reaction and the chemistry of the surrounding rock. An artificial reactor, or the detonation of a nuclear weapon, would produce a different distribution, different ratios of isotopes, different spatial patterns, different associations with other elements. The analytical techniques to detect these differences exist. They are used routinely in nuclear forensics and non-proliferation monitoring. Applying them to the deep geological record would require nothing more than a shift in perspective, a willingness to ask the question and fund the analysis. And yet the analysis has not been done. Not because it is technically impossible, but because the scientific community has not considered it worth doing. The assumption that intelligence is new, that technology is exclusively human, that the deep past is a wilderness of mindless organisms and purposeless chemistry. This assumption does not need to be defended, because it has never been challenged with sufficient institutional force to require a defense. It sits beneath the surface of every research program, every funding proposal, every peer review, shaping what questions are considered legitimate and what questions are dismissed as frivolous before they are even formulated. Schmidt and Frank understood this. Their paper was, in a sense, not just a scientific contribution, but a rhetorical one, an attempt to shift the Overton window of legitimate inquiry, to demonstrate that the question of prior technological species is not pseudoscience, but a genuine gap in our knowledge that can be addressed with existing tools and methods. They were not asking for belief, they were asking for investigation. They were pointing at a door that had always been there but that no one had thought to open and saying, we have the keys, we have the instruments, we have the methodology. All we lack is the decision to use them. The irony is that the decision to look would cost almost nothing in relative terms. The sediment cores already exist, thousands of them, pulled from ocean floors around the world by decades of deep-sea drilling programs. The mass spectrometers already exist. The isotopic databases already exist. What does not exist is the research program, the coordinated, funded, peer-reviewed effort to examine the deep geological record specifically for technosignatures. It's a search that has never been conducted, for a signal that may or may not be there, in a record that is fragmentary but not entirely silent. And until that search is conducted, the Silurian Hypothesis remains what it has always been. Not a claim, not a theory, not even a proper hypothesis in the strict scientific sense, but a question that sits at the intersection of geology, chemistry, astrobiology, and philosophy, waiting for someone to decide that it deserves an answer. But there is another version of this question, older, more famous, and in some ways more disturbing, that has been asked not about the Earth, but about the cosmos. A question that Enrico Fermi posed over lunch in 1950, and that has haunted the scientific imagination ever since. And when that question is turned inward, when it is applied not to the stars but to the stone beneath our feet, its implications become, if anything, more unsettling than they have ever been in their original astronomical form. The lunch took place at Los Alamos National Laboratory in the summer of 1950. The participants were 4 physicists, Enrico Fermi, Edward Teller, Herbert York, and Emil Konopinski. The conversation had drifted, as conversations among physicists often do, from the practical to the speculative. They'd been discussing recent reports of unidentified flying objects, a topic that, in 1950, had not yet acquired the stigma it would later carry. And this had led, naturally enough, to the question of extraterrestrial civilizations. At some point during the discussion, Fermi looked up from his lunch and asked a question so simple and so devastating that it has defined an entire field of inquiry ever since. Where is everybody? The question has become known as the Fermi paradox, though it is not, strictly speaking, a paradox. It is a tension, a dissonance between two observations that should, by all reasonable expectations, be consistent but are not. The first observation is that the universe is unimaginably vast and unimaginably old. The Milky Way alone contains an estimated 200 to 400 billion stars, many of which are older than the Sun, and many of which are now known to harbour planetary systems. The number of potentially habitable planets in the galaxy is measured in the billions. Given the immensity of these numbers and the billions of years of time available, the probability that intelligent, technologically capable life has arisen somewhere else seems, on the face of it, overwhelming. The second observation is that we have found no evidence of such life. No signals, no artifacts, no probes, no visits, nothing. The universe, as far as we can tell, is silent. This silence has generated an enormous literature of proposed explanations, the so-called solutions to the Fermi paradox. Perhaps intelligent life is far rarer than we assume. Perhaps civilizations inevitably destroy themselves before they can expand into the galaxy. Perhaps they exist but are deliberately hiding. Perhaps the distances between stars are simply too great for any form of communication or travel. Perhaps we are looking in the wrong way, at the wrong frequencies, in the wrong places. Each of these proposals has its advocates and its critics, and the debate shows no sign of resolution. The paradox endures. But in 2017, the astrophysicist Jason Wright at Penn State University published a paper that turned the Fermi paradox in a direction that few had previously considered. Wright's paper, titled Prior Indigenous Technological Species, appeared in the International Journal of Astrobiology, the same journal that would the following year publish Schmidt and Frank's Silurian Hypothesis paper. Wright's argument was disarmingly straightforward. Before searching for evidence of extraterrestrial technological civilizations on other worlds, we should consider whether such evidence might exist closer to home, not just on Earth, but within our own solar system, on Mars, on Venus, on the moons of the outer planets, or buried in the asteroid belt, and most provocatively on Earth itself. Wright's reasoning was rooted in the same observation that animated the Silurian Hypothesis. The geological record of our planet is radically incomplete, and the processes of tectonic recycling, erosion, and metamorphism would destroy virtually all physical evidence of a prior technological species within a few tens of millions of years. But Wright extended the argument beyond geology into a broader philosophical framework. He pointed out that the Fermi paradox is typically framed as a question about interstellar distance and the probability of contact between civilizations separated by light years of empty space. But if intelligence can arise more than once on a single planet, or within a single solar system, then the paradox acquires a temporal dimension that is usually ignored. The silence we attribute to the vastness of space may, in part, be a solace of time, the silence of civilizations separated not by distance but by millions of years, arising and vanishing on the same world without ever overlapping, without ever knowing of each other's existence. This is the Fermi paradox turned inward, and its implications are profoundly disorienting. We are accustomed to thinking of the search for intelligent life as an outward-looking endeavour, a matter of radio telescopes and space probes and the patient scanning of distant star systems. But Wright and independently Schmidt and Frank suggested that the search might need to begin much closer to home, not in the electromagnetic spectrum of a distant galaxy, but in the geochemistry of a sediment core pulled from the floor of the Pacific Ocean, not in the infrared signature of an alien megastructure, but in the isotopic ratios of a layer of Paleocene limestone. The tools are different, the scale is different, but the question is the same. Is there evidence anywhere that a technological civilization existed before our own? The temporal version of the Fermi paradox is in some ways more troubling than the spatial one. The spatial paradox can be resolved by invoking distance. The galaxy is large, and perhaps civilizations are simply too far apart to communicate. But the temporal paradox cannot be resolved by distance. It applies to a single planet, our planet, and its resolution depends not on the vastness of space but on the depth of time and the completeness of the geological record. And as has been established, the geological record is not complete. It is spectacularly, systematically, almost aggressively incomplete. The Earth consumes its own past with a thoroughness that borders on the artistic. And so the temporal silence, the absence of evidence for prior intelligence on this planet, carries the same ambiguity as the spatial silence. It may reflect a genuine absence, or it may reflect the limits of our abilities to detect what was once there. There is a further dimension to this that Wright explored and that deserves consideration. If intelligence has arisen multiple times on Earth, or even once before in any form, then the Fermi paradox acquires a recursive quality that is almost vertiginous. Each prior civilization, if it existed, would have faced its own version of the paradox. It would have looked at the sky and seen the same silent stars. It would have looked at the ground and found no evidence of any predecessor. It would have concluded, as we have concluded, that it was alone, the first and only technological species in the history of its world. And it would have been wrong just as we might be wrong. The paradox does not resolve itself, it deepens. It becomes a hall of mirrors, each civilization reflecting the same silence back at the one that follows, each one believing itself to be the first because the evidence of its predecessors has been consumed by the patient machinery of geological time. This is not merely a scientific proposition, it is at its core an epistemological one, a question about the limits of knowledge itself. How much can we know about the deep past? What are the boundaries of the knowable? And when we reach those boundaries, what do we do with the space beyond them? The space that is not empty, but simply dark, not answered, but simply unasked? The Silurian Hypothesis does not claim to have crossed those boundaries. It claims to have found them. It claims to have stood at the edge of what science can currently resolve, and to have noticed that the darkness beyond is not featureless but structured, shaped by the specific gaps in the geological record, the specific limitations of preservation, the specific biases of the analytical tools we've chosen to deploy. And it is here that the question ceases to be purely scientific and becomes something else, something that touches on the way we construct meaning, the way we tell stories about ourselves, the way we locate our species in the vast and largely unknown history of the planet we inhabit. Because the assumption that we are first, that intelligence is new, that the deep past was mindless and mute, is not just a scientific hypothesis. It is a narrative. It's a story we tell ourselves about who we are and where we stand in the hierarchy of nature. It is comforting in the way that all origin stories are comforting. It places us at the apex, the culmination, the point toward which everything has been building. And the Silurian Hypothesis, gently and without malice, suggests that this story may be less a description of reality than a reflection of our own need to be central, to be singular, to be the protagonist of a story that may have had many protagonists before us, none of whom left a forwarding address. Fermi's question, "Where is everybody?" was directed at the stars, but the stars, whatever they hold, are far away. The ground beneath our feet is not, and it is the ground that holds the deeper version of the question, not where is everybody, But where was everybody? Where are the traces of the minds that might have preceded us? Where are their chemical ghosts, their esotopic shadows, their faint molecular fingerprints in the compressed darkness of ancient stone? The silence of the cosmos is vast and well documented, but the silence of the Earth, the silence of 4.5 billion years of geological history, most of it unexamined, much of it unexaminable, is vaster still. And somewhere in that silence, buried beneath the assumptions of a civilization that has never seriously questioned its own primacy, there may be an answer, or there may be only more silence. But the difference between the two, between an answer and a silence, cannot be determined without looking, and the looking, for the most part, has not yet begun. What has begun, however, is something older than science and more persistent than methodology. It is the human habit of encoding the distant past in story, in myth, in cosmology, in the layered narratives of cultures separated by oceans and millennia, yet haunted by the same recurring images. Images of worlds destroyed and rebuilt, of knowledge gained and lost, of cycles that turn and return, carrying the memory of what came before, not in rock or chemistry, but in language, in symbol, in the architecture of belief. And it is to these stories, these ancient, half-remembered, stubbornly persistent stories, that the inquiry must now turn, not as evidence in the scientific sense, but as something that may be equally important. A record of remembering that predates every instrument we have ever built. A record of remembering that predates every instrument, and perhaps every civilization we have ever known. Long before the first geologist cracked open a rock and read the story written in its layers, long before the first chemist measured the ratio of isotopes in a grain of ancient sediment, human beings were already telling stories about the deep past. Not geological stories, not scientific stories, stories woven from image and metaphor and ritual repetition, passed from mouth to ear across generations so numerous that the origin of the telling itself was forgotten. These stories were not treated as hypotheses, they were treated as truths, sacred truths, foundational truths, truths so important that they were embedded in the architecture of religion, law, and identity. And what is remarkable, what has never been adequately explained, is that so many of these stories, arising independently in cultures separated by vast distances and millennia of isolation, tell essentially the same tale. A tale of worlds that existed before this one, a tale of destruction and renewal, a tale of knowledge possessed, lost, and only dimly remembered. The Hindu cosmological tradition is perhaps the most elaborately developed expression of this theme. In the Vedic and Puranic texts, time is not linear, but cyclical, organized into vast repeating units called yugas. The 4 yugas, Satya, Treta, Dvapara, and Kali, form a single Mahayuga, a great cycle of approximately 4.32 million years, which itself is embedded within larger cycles of almost inconceivable duration. Each yuga represents a progressive decline from a golden age of truth and righteousness to a dark age of ignorance and corruption, culminating in dissolution and renewal. The Satya Yuga, the first and longest age, is described as an era in which human beings, or beings resembling humans, possessed extraordinary knowledge, lived for immense spans of time, and existed in harmony with cosmic law. With each successive age, this knowledge diminishes, lifespans shorten, and the world decays until the cycle resets and the process begins again. What is striking about the Yuga system is not merely its antiquity. The earliest Vedic texts date to at least the 2nd millennium before the Common Era, and the oral traditions they encode are certainly older, but its structural resonance with the geological concept of deep time. The timescales involved are not mythological approximations of human history. They are enormous, spanning millions of years, dwarfing the recorded history of any civilization, and the pattern they describe, cycles of emergence, flourishing, decline, and destruction, repeated endlessly, mirrors, in narrative form, the pattern that the geological record reveals, a planet on which complex life has arisen, been devastated by mass extinctions, and arisen again, each time in forms that bear only partial resemblance to what came before. The Hopi people of the American Southwest possess a cosmological tradition that is structurally similar, though culturally and geographically entirely independent. In the Hopi creation narrative, the world has been created and destroyed multiple times. The current world, the fourth world, was preceded by 3 earlier worlds, each of which was destroyed because its inhabitants fell into imbalance, corruption, or forgetfulness. The first world was destroyed by fire. The second world was destroyed by ice. The third world was destroyed by flood. In each case, a small number of beings survived the destruction and carried the memory of the previous world into the next, serving as the seed from which the new world would grow. The survivors were guided by spiritual beings, sometimes called kachinas, sometimes described in terms that resist easy translation, who preserved the knowledge necessary for the continuation of life. The parallels with the geological record are not exact, and that they should not be forced into a scientific framework they were never intended to occupy. But the structural correspondence is difficult to ignore. Fire, ice, and flood are not arbitrary choices. They are, in fact, the 3 primary mechanisms by which the Earth has repeatedly devastated its own biosphere: volcanic cataclysm, glaciation, and marine transgression. That an indigenous culture with no access to geological science should encode these 3 mechanisms into its deepest cosmological narrative is, at minimum, worthy of contemplation. It may reflect nothing more than the universal human experience of natural disaster, magnified and mythologized over centuries of retelling. Or it may reflect something else, a thread of memory, impossibly attenuated but not entirely severed, reaching back towards events that occurred long before the culture itself existed. And then there is Plato. In 2 dialogues, the Timaeus and the Critias, written in approximately 360 before the Common Era, Plato describes a powerful and technologically advanced civilization called Atlantis, which existed 9,000 years before the time of the Athenian statesman Solon, placing it roughly in the 10th millennium before the Common Era. Atlantis, according to Plato's account, was a maritime empire of extraordinary wealth and sophistication, centered on an island larger than Libya and Asia combined, located beyond the Pillars of Hercules, the Strait of Gibraltar. The Atlanteans possessed advanced engineering, monumental architecture, a complex system of governance, and access to a mysterious metal called orichalcum, and they were destroyed suddenly and completely by a catastrophic event. Earthquakes and floods that caused the island to sink beneath the sea in a single day and night of misfortune. The historicity of Atlantis has been debated for over 2,000 years, and the weight of scholarly opinion holds that it was a philosophical allegory, a literary device used by Plato to illustrate moral and political arguments about the corruption of power and the hubris of civilization. This interpretation is well supported by the context of the dialogues and by Plato's well-known use of myth as a pedagogical tool, and yet the story has proven extraordinarily resistant to dismissal. It has been taken up, reinterpreted, and elaborated by countless writers, researchers, and explorers from the ancient world to the present day, each one convinced that behind the allegory lies a kernel of historical truth, a memory of a real civilization, a real catastrophe, a real loss. What is less often noted is the framing of the story within the dialogues themselves. Plato does not present the account of Atlantis as his own invention. He attributes it to Solon, who allegedly heard it from Egyptian priests at the Temple of Neith in Sais. The priests, according to the narrative, told Solon that the Greeks were like children, that they had no memory of the distant past because their civilization had been repeatedly destroyed by fire and flood, and that only Egypt, protected by the Nile and by geographical fortune, had preserved the records of earlier ages. The implication is not merely that Atlantis existed, but that the loss of civilizational memory is a recurring phenomenon, that knowledge is fragile, that history is periodically erased, and that the ignorance of the present is not a natural condition but the result of catastrophic interruption. The Sumerian king list offers yet another variation on this theme. This ancient text, preserved on several clay tablets dating to approximately the early 2nd millennium before the Common Era, records the rulers of Sumer from the beginning of kingship, which it places before the Great Flood. The antediluvian kings, according to the list, reigned for periods of astonishing length, tens of thousands of years each, with individual reigns lasting 28,000, 36,000, or even 43,000 years. After the flood, the reign lengths declined dramatically, approaching historically plausible durations. The standard scholarly interpretation is that the antediluvian figures are mythological, exaggerated, symbolic, or based on misunderstood numbering systems, and this interpretation is probably correct. But the structure of the list, a golden age of immense duration interrupted by a global catastrophe, followed by a diminished age in which knowledge and power are reduced, echoes the same pattern found in the Hindu Yugas, the Hopi creation narrative, and the Platonic account of Atlantis. The Greek tradition of the ages of man, articulated most fully by the poet Hesiod in the 8th century before the Common Era, follows an identical arc. Hesiod describes 5 successive ages: gold, silver, bronze, heroic, and iron, each representing a progressive decline from an original state of perfection and harmony with the divine. The Golden Age was a time without labour, suffering, or death. The Silver Age brought foolishness and the neglect of the gods. The Bronze Age brought war. And the Iron Age, Hesiod's own time and ours, is an era of toil, injustice, and decay, which will end only when the gods destroy it and begin the cycle anew. These are not scientific documents. They are not evidence in any empirical sense. They cannot be carbon dated or subjected to isotopic analysis. And yet they share a structure so consistent, across cultures so distant and so independent, that the consistency itself becomes a datum, not a proof, but a pattern that demands interpretation. Why do so many unrelated cultures, on so many continents, across so many centuries, tell stories of prior worlds that were more advanced, more knowledgeable, and more connected to cosmic forces than our own? Why do they consistently describe a pattern of decline, from a golden age to a dark age, from fullness to fragmentation, from knowledge to forgetting? And why do they so often locate the mechanism of transition and catastrophe, flood, fire, the wrath of gods, or the indifference of nature, rather than in the gradual linear progression that modern historiography assumes? One answer is psychological. These myths reflect the universal human tendency to idolize the past and to project anxieties about the present onto a narrative of decline. This is a valid interpretation, and it accounts for much of the mythological material. But it does not account for all of it. It does not explain the specificity of the catastrophic mechanisms. It does not explain the consistency of the cyclical structure. And it does not explain why these myths, in so many cultures, are treated not as stories but as histories, as records of events that actually occurred, transmitted across generations by custodians who regarded the preservation of this knowledge as a sacred duty. There is another possibility, one that cannot be proven but that the Silurian Hypothesis makes thinkable. What if these myths are not inventions? What if they are not allegories, not projections, not psychological archetypes dressed in narrative clothing? What if they are instead the scar tissue of a species that has forgotten what it once knew? The distorted, degraded, but not entirely extinguished memory of worlds that actually rose and fell, of knowledge that was actually gained and lost, of catastrophes that actually erased the record and left behind only the faintest trace in the one medium that survives the destruction of all others, the human voice, passing its burden from one generation to the next, growing faint with each telling but never quite falling silent. This is not a conclusion, it is a question. The kind of question that sits at the boundary between science and something older, something that does not have a name in the vocabulary of modern inquiry. And it is with this question still resonating, still unresolved, still echoing through the long corridors of deep time and human memory, that the journey approaches not its end, but its edge. The place where the known gives way to the unknown, where the measured gives way to the immeasurable, and where the only honest response is not an answer but a silence held open, attentive and unafraid. Somewhere beneath the surface of the earth, at a depth where sunlight has never reached and never will, there is a layer of rock that was once the floor of an ocean that no longer exists. It was deposited grain by grain, molecule by molecule over millions of years, in waters that teemed with life forms that left no descendants and bore no names. The pressure of everything that accumulated above it, sediment, stone, time, compressed it into a darkness so complete that even the atoms within it have been rearranged, their original configurations overwritten by the slow thermodynamic imperatives of burial. Whatever story that layer once told has been translated into a language that may no longer be readable, not erased exactly, transformed, folded into the planetary body like a memory folded into sleep and still present perhaps, but no longer accessible to the waking mind. This is what the Earth does with its past. Not all of it, not always, but enough of it, and often enough, that the past becomes less a record and more a palimpsest. A surface scraped and rewritten so many times that only the faintest impressions of the earliest texts remain, visible not as words but as ghosts of words, as the pressure marks left by a stylus on a tablet that has since been smoothed and inscribed with something else entirely. The geologist reads the palimpsest with instruments of extraordinary sensitivity, mass spectrometers, electron microscopes, magnetometers, and recovers fragments of the overwritten text. But the fragments are scattered, ambiguous, and surrounded by vast blank spaces that cannot be filled because the material that once filled them has been recycled into the body of the planet, melted and reconstituted in the slow furnace of the mantle, emerging millions of years later as fresh basalt on some distant ocean ridge, carrying no memory of what it was before. The Silurian Hypothesis asks whether one of those blank spaces, one of those erased passages in the palimpsest, might once have contained the record of a mind, not a human mind, not necessarily a mind anything like ours, but a mind nonetheless, a system of sufficient complexity to observe its environment, to manipulate it deliberately, to wonder about it, and perhaps to record its wanderings in some medium that the Earth has since consumed. The hypothesis does not answer this question. It cannot. No one can with the evidence currently available. What it does is something more fundamental and more unsettling. It demonstrates that the question is legitimate, that it is not foolish, not pseudoscientific, not the province of conspiracy theorists and late-night television. It is a question that arises naturally from the intersection of what we know about the incompleteness of the geological record, the fragility of material culture on geological timescales, the convergent tendency of evolution toward cognitive complexity, and the deep cyclical history of catastrophe and renewal that defines life on this planet. And the question once asked does not confine itself to science. It spreads like water finding cracks in stone into the broader landscape of how we understand ourselves. Because the assumption that we are first, that the 4.5 billion years of Earth's history before us were a mindless prelude to our arrival, is not merely a scientific hypothesis. It is a founding myth. It is the story that modern civilization tells itself about its own significance, its own uniqueness, its own place in the order of things. And like all founding myths, it serves a purpose that is not entirely rational. It provides comfort. It provides meaning. It provides the assurance that our struggles, our achievements, our suffering and our beauty are not just important but unprecedented, that nothing like us has ever existed before, and that our story is therefore not a repetition, but an origin. The Silurian Hypothesis does not destroy this myth. It merely illuminates it, holds it up to the light and shows the threads of assumption woven through it, the places where confidence is mistaken for evidence, where tradition is mistaken for truth. It asks us to consider the possibility that we are not the protagonists of a story, but the latest characters in a narrative far longer and far stranger than we have imagined. A narrative in which minds have arisen and vanished, civilizations have flourished and been erased, and the Earth has continued its slow revolution through space and time, indifferent to the dramas enacted on its surface, recording nothing deliberately, preserving nothing by design, offering to those who come after only the thinnest, most accidental, most ambiguous remnants of what came before. There is a term in Japanese aesthetics, mono-no-aware, that translates roughly as the pathos of things, the bittersweet awareness of impermanence. It is the feeling evoked by cherry blossoms falling, by the last light of autumn, by the recognition that everything beautiful is beautiful in part because it will not last. The Silurian Hypothesis evokes something similar, but on a scale so vast that the emotion it produces has no established name. It is the awareness that not just individual lives or individual civilizations, but entire lineages of intelligence may be impermanent, may arise, flourish, produce wonders that we cannot imagine, and then vanish so completely that even their vanishing leaves no trace. It is the pathos not of things, but of worlds. The awareness that the universe may be populated not with eternal civilizations, but with brief, bright flares of consciousness, separated by immense gulfs of darkness and silence, each one believing itself to be the first, each one unable to detect the others, each one destined to be forgotten by the very planet that gave it birth. This is not a despairing thought. Or rather it need not be. There is another way to hold it, not as a diminishment of human significance, but as an expansion of the frame within which significance is measured. If intelligence is not unique to us, if it is a recurring pattern in the deep history of this planet, then we are not alone in the most profound sense imaginable. Not alone in space, perhaps, but more importantly, not alone in time. We are part of a lineage of minds, a succession of awakenings, each one different, each one shaped by its own circumstances and its own biology, but each one reaching toward the same fundamental questions. What is this place? How did we come to be here? What came before? And what will remain when we are gone? The answers to these questions may never be fully known. The geological record is too incomplete, the mechanisms of erasure too efficient, the timescales too vast for certainty in either direction. We may never find the chemical ghost of a Paleocene civilization in a deep-sea sediment core. We may never identify the isotopic fingerprint of Mesozoic industry in a layer of ancient limestone. We may never recover, from the compressed darkness of Carboniferous coal, the molecular signature of a mind that burned with purpose 300 million years before our own. The absence may be real, the silence may be genuine, the deep past may be exactly what the textbooks describe, a world of mindless organisms governed by chemistry and physics and the blind mechanics of natural selection, producing complexity without awareness, beauty without perception, meaning without anyone to perceive it. Or the silence may be an artifact of our own limitations, a product of the questions we have failed to ask, the analyses we have failed to perform, the assumptions we have failed to examine. The geological record is not a closed book. It is an open one, vast and largely unread, written in a script that we are only beginning to decipher. And somewhere in its pages, in a stratum of Eocene clay, in a vein of Permian halite, in the molecular architecture of a Carboniferous coal seam, there may be a sentence that changes everything. A sentence written not in words, but in isotopes, not in language, but in chemistry, not by human hands, but by hands or appendages, or structures that we have never imagined and may never be able to reconstruct. A sentence that says simply and without elaboration, we were here. The night is deep now. The questions have been laid out, not as arguments to be won, but as paths to be walked, slowly in the dark with the patience that the subject demands. The earth turns, as it has always turned, carrying on its surface the thin, temporary, astonishingly improbable phenomenon of minds that can contemplate their own impermanence. Beneath those minds, beneath the cities and the roads and the ploughed fields and the ocean floors, the rock continues its slow descent into the mantle, carrying with it whatever secrets it holds, surrendering them to the heat, releasing them into the undifferentiated flow of planetary matter from which new rock will one day rise, clean and blank and ready to receive whatever impression the next world chooses to make upon it. The stone remembers nothing. The stone forgets everything. And yet, for reasons that geology cannot explain, and biology cannot fully account for, something keeps rising from the stone, something that opens its eyes, looks around and asks, "Was anyone here before me?" The question echoes through deep time, unanswered, perhaps unanswerable, bouncing off the walls of an empty chamber that may not be empty at all but merely dark. And in the darkness, in the silence between the last echo and the next, the earth holds its breath, not waiting, because the earth does not wait, but simply being as it has always been, vast and patient and full of things it has never been asked to reveal. The layers settle, the pressure builds, the silence deepens, and somewhere in a formation that has not yet been drilled, in a core that has not yet been pulled, in a spectrum that has not yet been analysed, a molecule sits in the dark, ancient, anomalous, alone, holding in its bonds the answer to a question that no one has yet thought to ask in quite the right way, in quite the right place, at quite the right depth. It does not call out. It does not signal. It simply exists, as it has existed for longer than any mind on the current surface of the earth can comprehend, waiting with the infinite patience of chemistry for the moment when a mind, reaching down through the layers of time and stone and assumption, finally arrives at the right depth, extends the right instrument, and reads what has been written there all along, or finds nothing and must learn to live with the silence and with the vastness of what can never be known.